Good evening, and welcome to The Gentle Scientist. If you found your way here tonight, perhaps you're seeking something different, something that helps you drift away. A gentle voice in the darkness, a story vast enough to put your own worries into perspective. Tonight, I want to take you on a journey through our home galaxy, the Milky Way, not with dramatic urgency, but with the quiet wonder it deserves. So, settle in. Find a comfortable position. Let your body sink into wherever you're resting. Dim the lights or turn them off entirely. Close your eyes if that feels right, or let them rest softly on the screen. There's nothing you need to do, nowhere you need to be. For the next few hours, you can simply exist, letting your breathing slow, your muscles release their tension, your thoughts gradually quiet as we drift together through the cosmos. Tonight, we'll explore the Milky Way from the inside out, and I'll tell you gently, slowly, letting each fact settle like a soft blanket, giving your mind something to rest on as sleep gradually approaches. Before we begin, if you're enjoying this kind of content, I invite you to subscribe to The Gentle Scientist. Leave a like on this video if it helps you find rest. And in the comments, tell me, what time is it where you are? What part of the world are you listening from? How are you feeling tonight? Now, let everything else fall away. Let your plans wait until tomorrow. For now, just breathe, just listen, just rest. Let's begin. Look up on a clear night, far from the glow of cities, and you might see it. A pale river of light flowing across the darkness, so faint it almost isn't there, so vast it stretches from horizon to horizon. That soft, luminous band, dusty and distant, is not something out there in the void. It is home. You are inside it, woven into its structure, carried along by its motion. Every atom in your body, every breath you take, every thought drifting through your mind as you settle into rest tonight, all of it belongs to the Milky Way. We do not observe our galaxy from some distant vantage point, a telescope trained on a spiral of stars, light years away. We live within it, embedded, hidden inside one of its arms, like a single cell within a body too large to comprehend. And from this position, tucked into the fabric of the galaxy itself, we try to understand the whole. It is like standing in the middle of a vast forest, surrounded by trees in every direction, and attempting to draw a map of the entire woodland. You can see the trunks nearby, the canopy above, the shadows between. But the full shape, the boundaries, the way it curves and sprawls across the land, all of that remains hidden, inferred, pieced together slowly through observation, mathematics, and wonder. Our address in this cosmic city is specific, though it took humanity millennia to discover it. We live approximately 26,000 light-years from the galactic center, not at the heart, where stars crowd so densely they could cast shadows at night. Not in the outer halo, where ancient wanderers drift in silence through the dark. We live in what astronomers might call the suburbs, a comfortable, relatively quiet region where star formation proceeds at a modest pace, where supernovae are infrequent enough not to sterilize every world, where the density of matter allows for stability, for planets, for the long, slow emergence of complexity and life. More precisely, we reside in a structure called the Orion Spur, sometimes known as the Orion Arm, though to call it an arm overstates its grandeur. It is a minor branch, a spur connecting two of the galaxy's more prominent spiral arms, Perseus and Sagittarius. Think of it as a side street between major avenues, less trafficked, less dramatic, but no less real. The Orion Spur stretches for about 10,000 light-years, populated by familiar stars, Betelgeuse and Rigel in Orion, Aldebaran in Taurus, the Pleiades cluster glittering like scattered diamonds. These are our neighbors, the landmarks of our local cosmic neighborhood. And among them, unremarkable in brightness or size, orbits a single yellow dwarf star, the Sun, carrying with it a retinue of planets, moons, asteroids, and one small blue world where, for a brief moment in cosmic time, life has learned to look up and ask questions. Why does our location matter? In the grand architecture of the galaxy, position determines fate. Too close to the center, and the environment becomes hostile. Radiation levels spike. Supernovae erupt more frequently, their shock waves tearing through stellar nurseries and planetary atmospheres alike. The central black hole, though distant, exerts its influence, stirring the surrounding stars into chaotic orbits. Gravitational interactions between densely packed stars can fling planets from their systems or send comets careening inward. Life, if it emerges at all, would face relentless bombardment, sterilization, extinction. Too far from the center, and the galaxy grows sparse, thin, impoverished. Out in the distant halo, or the ragged edge of the disk, stars are scattered like distant lanterns. Heavy elements, those building blocks forged in stellar cores and scattered by supernovae, carbon, oxygen, nitrogen, iron, are rare. Worlds that do form may be barren, lacking the chemical complexity necessary for life. The universe out there is older, quieter, and simpler, beautiful in its emptiness, but less conducive to the intricate chemistry that builds molecules, cells, awareness. We live, instead, in what some scientists call the galactic habitable zone, a broad band circling the galaxy at a comfortable radius, neither too close nor too far, where conditions are just right. Here, stars have access to the enriched gas of earlier generations. Here, the pace of stellar birth and death creates abundance without catastrophe. Here, planets can form with the ingredients they need, orbit in relative peace for billions of years, and perhaps, as on Earth, nurture the slow unfolding of life. But even in this tranquil suburb, we are not still. Nothing in the galaxy is still. Our sun, pulling its family of planets along, races through space at a speed that defies human intuition. 828,000 kilometers per hour, 230 kilometers every single second. Fast enough to circle the Earth in less than 3 minutes. And yet, sitting here, reading or resting, you feel nothing. No wind, no acceleration, no sense of the tremendous velocity carrying you forward. The motion is so smooth, so constant, that it becomes invisible. The Earth spins. The Earth orbits the sun. and the sun sweeps through the galaxy in a great looping path. And all of it happens in silence, in stillness, as if the universe itself were holding its breath. This journey the sun makes around the galactic center is not a quick lap. It is an odyssey, measured not in years or centuries, but in epochs. A single orbit takes approximately 225 to 250 million years. Astronomers call this a galactic year, a unit of time so vast it redefines patience. In all of its 4.6 billion years of existence, the Sun has completed only about 20 orbits. 20 circuits around the luminous heart of the galaxy, 20 times rising through spiral arms and drifting into the quiet spaces between. 20 long, slow revolutions since its birth in a collapsing cloud of gas and dust. Think for a moment about what this means. The last time our solar system was in this particular part of its orbit, roughly 225 million years ago, the world looked nothing like it does today. There were no humans, no mammals, no birds in the sky. The continents were fused into a single, massive landmass, Pangaea, and the climate was hot, arid, and harsh. The first dinosaurs were just beginning to appear, small, nimble creatures that would, over the coming millennia, rise to dominate the Earth. And the stars overhead, the constellations, the familiar patterns we use to navigate the night sky, were different. The sun was in a different region of the galaxy. Different stars shone nearby. Different nebulae glowed in the distance. The cosmic neighborhood was not the same. Before that, 2 galactic years ago, about 450 million years in the past, life on Earth was only beginning to venture onto land. Fish swam in ancient seas, but the continents were barren, lifeless rock and sand. The sun orbited through the galaxy under an alien sky, pulling its planets through a universe that had never known forests, never known footsteps, never known the sound of wind through leaves. And further back still, 3 galactic years ago, Earth itself was young, molten, still cooling from its violent formation. The moon had recently been born from a colossal impact, and the surface of the planet was a hellscape of lava and steam. The sun, freshly ignited, had just begun its first orbit around the Milky Way, carrying with it a newborn solar system, still finding its balance. Every orbit brings the sun through different regions of the galaxy. As it moves, the stellar neighbors change. Stars that once shone brightly nearby drift away on their own paths. New stars emerge from collapsing clouds. Some explode as supernovae, briefly outshining entire galaxies before fading into remnants. Others, smaller and dimmer, settle into long, quiet lives that will last trillions of years. The galaxy is not a static backdrop. It is a dynamic, ever-changing system, and we are travelers within it, carried along by motion too vast and too slow for us to perceive directly. As the sun orbits, it also bobs gently up and down through the galactic plane, rising above it, then sinking below, in a slow, vertical oscillation that takes tens of millions of years. This motion, driven by the gravitational pull of the disk's mass, causes the solar system to cross the mid-plane of the galaxy periodically. Some researchers have wondered whether these crossings might correlate with extinction events on Earth, as increased exposure to cosmic rays or gravitational disturbances from passing stars could influence climate or trigger comet showers. The evidence is not conclusive, but the idea is tantalizing. Even our vertical, drifting through the galaxy's thin plane might shape the story of life on our world. We are passengers, then, on multiple journeys. The Earth spins on its axis, once every 24 hours, carrying us through day and night. The Earth orbits the Sun, once every 365 days, tracing an ellipse through the inner solar system. The Sun orbits the galactic center, once every 225 million years, sweeping through spiral arms and quiet lanes alike. And the Milky Way itself moves through intergalactic space, pulled by the gravity of other galaxies, drifting through the local group, bound for an eventual collision with Andromeda, billions of years in the future. There is no cosmic stillness, no fixed point of reference. Everything moves in relation to everything else, nested within nested motions, wheels within wheels. The galaxy does not spin like a solid disk. Different parts rotate at different speeds. The inner regions move faster, completing orbits in just a few million years. The outer edges drift more slowly, taking 500 million years or more to circle once. And threaded through all of this is the invisible scaffolding of dark matter, holding the structure together, providing the gravitational framework that prevents the galaxy from flying apart. From this place, 26,000 light-years from the center, tucked into the Orion Spur, we look outward and inward, trying to understand the architecture of our home. We cannot step outside it, cannot see it from afar as we see other galaxies, distant spirals, and ellipticals frozen in telescope images. We are part of the structure we are trying to map, embedded within the very thing we seek to comprehend. And yet, through centuries of patient observation, through the careful tracking of stars and gas, through radio telescopes peering through dust and infrared instruments revealing hidden light, we have begun to sketch the shape of the Milky Way. We have learned where we are, how fast we are moving, and what forces guide our path through the cosmos. This knowledge, hard-won and still incomplete, carries with it a strange kind of comfort. We are not adrift in a void. We are part of something, a vast structure of matter and energy, organized by gravity and time, spinning slowly through the universe. Our lives unfold within it. Our histories are shaped by it. Every journey we take, every step we make, happens while carried along by the galaxy's motion. And though we cannot feel it, though it remains hidden beneath the ordinary sensations of daily life, we are always moving, always traveling, always part of a journey that began billions of years ago and will continue long after we are gone. So tonight, as you rest, as your breathing slows and your thoughts begin to soften and drift, remember where you are. Not just in a room or a city or on a planet, but in the Orion Spur, 26,000 light-years from the galactic center, orbiting at 828,000 kilometers per hour through a galaxy that has been our home since the sun first ignited. You are part of this, woven into its light. And as you fall asleep, the galaxy carries you forward, gently, silently, through the night, drifting through this quiet suburb of the galaxy, carried on our long orbital journey. There's something we can do that no satellite, no space probe, no distant telescope can replicate. We can simply look up, with nothing but our eyes, no instruments, no technology, just the same vision our ancestors possessed tens of thousands of years ago. We can see the Milky Way, not as data, not as coordinates or measurements, but as light. Pure, ancient, beautiful light stretching across the darkness above us. How many of us, I wonder, have seen it? Really seen it? Not the washed-out glow above a city, where a handful of bright stars peek through the haze of artificial light, but the true Milky Way, revealed in its full glory from a place where darkness still exists. Perhaps you've stood on a mountain peak, or walked along a beach, far from town, or found yourself in a desert where the night sky opens like a gateway. If you have, you know the feeling. That moment when your eyes adjust and suddenly, there it is. A river of light flowing overhead, so faint it seems almost like a trick of vision, but so vast it fills half the sky. That hazy band, that soft luminous streak, is not something distant and separate from us. It is us. It is our galaxy, seen from within. Every photon reaching your eyes has traveled across light years of space, emitted by stars you will never know the names of, scattered by dust clouds older than civilization, arriving here, now, in this moment, to touch your retina and be translated by your brain into wonder. The name itself, Milky Way, comes from ancient Greece. They looked up and saw that pale band and imagined it as milk spilled across the heavens. In their mythology, the infant Heracles, son of Zeus, was placed at the breast of the sleeping goddess Hera. He suckled so forcefully that milk sprayed into the sky, creating the glowing river we see today. It's a beautiful story, poetic and strange, but like so many ancient tales, it was an attempt to explain something profound that they could see but not yet understand. Other cultures had their own names, their own stories. The Norse called it the Path of Ghosts, the road traveled by souls on their way to the afterlife. In East Asia, it was the Silver River, a celestial waterway separating star-crossed lovers. Aboriginal Australians saw it as a river in the sky world where ancestral spirits traveled, or in some stories, as a great emu outlined by the dark dust lanes against the light. These stories are as varied as humanity itself, but they share something essential. They all recognized that this band of light was special, different from the scattered stars, something that demanded explanation, meaning, reverence. For most of human history, we saw the Milky Way every night. It was part of the sky, as familiar as the moon, as constant as the seasons. Our ancestors planned harvests by it, navigated by it, told stories under it. They knew its shape intimately, how it arched differently through summer and winter, how it rose and set, how certain stars clustered along its path. It was woven into the fabric of their lives in ways we've largely lost. Because here's a strange and sad truth. Most people alive today have never seen the Milky Way. Not really. Light pollution has stolen it from us. Cities glow so brightly now that they drown out the faint light of our own galaxy. Estimates suggest that more than 80% of the world's population lives under light-polluted skies. In North America and Europe, that number rises to 99%. We have, in the span of just a few generations, erased the night sky that guided and inspired humanity for hundreds of thousands of years. But if you are fortunate enough to escape the glow, if you drive far enough into the countryside or climb high enough into the mountains, the Milky Way returns. And when it does, it changes something. There's a reason that people who see it for the first time often fall silent. The scale becomes real in a way that words and images can never quite convey. You are looking at billions of stars, their light merged into a continuous glow. You are seeing depth, structure, the architecture of a galaxy rendered in shades of silver and shadow. What exactly are you seeing when you look at that band? You're seeing stars, hundreds of billions of them, so distant that your eyes cannot resolve them individually. They blur together into that milky luminescence. Most of what you see are stars in the galactic disk, the flat plane where most of the Milky Way's stellar population resides. When you look along the band, you're looking through the longest stretch of this disk, through the densest concentration of stars, peering down the length of the spiral arms from your position within them. But you're only seeing a tiny fraction of what's actually there. Astronomers estimate that with the naked eye, even under perfect conditions, you can see perhaps 3,000 to 5,000 stars. That sounds like a lot. It feels like a lot when you're standing beneath them. But the Milky Way contains somewhere between 100 billion and 400 billion stars. The exact number is uncertain, lost in the haze of distance and dust. What you see with your eyes represents perhaps 0.0003% of the galaxy's total stellar population. A whisper, a hint, the faintest suggestion of the whole. And even that whisper is filtered, edited by the universe itself. Interstellar dust, microscopic grains of carbon and silicates scattered throughout the galaxy, absorbs and scatters starlight. In visible wavelengths, this dust acts like a fog, obscuring everything behind it. Vast regions of the galaxy are completely hidden from our optical view, entire stellar populations invisible, shrouded behind curtains of cosmic soot. The center of the galaxy, that dense luminous core 26,000 light-years away, is blocked almost entirely. Invisible light, we cannot see it at all. The dust is too thick, the extinction too complete. This is why astronomers use other wavelengths. Infrared light, with its longer wavelengths, can slip through dust more easily. Radio waves penetrate even further, revealing the cold hydrogen gas that traces the galaxy's structure. X-rays and gamma rays show the hot, violent processes, supernovae and black holes and colliding stellar winds. Every wavelength tells a different story, reveals a different layer of the Milky Way's complexity, but none of them, no matter how sophisticated, can replicate the simple human experience of standing under a dark sky and seeing that band of light with your own eyes. The appearance of the Milky Way changes with the seasons. In summer, from the northern hemisphere, the densest, brightest part of the band rises above the southern horizon. This is the direction toward the galactic center, toward Sagittarius, where stars crowd most thickly. The Milky Way here is bright, textured, broken by dark rifts where dust lanes cut across the light. You can see structure in it, lanes and clouds, the suggestion of depth and form. It feels alive, almost three-dimensional, a landscape painted in starlight. In winter, the Milky Way still arcs overhead, but it's fainter, thinner, less dramatic. This is the view looking outward, away from the center, toward the outer edges of the galaxy where stars are more scattered. It's still beautiful, still profound, but quieter somehow. Less insistent, a gentler presence in the sky. From the southern hemisphere, the view is even more spectacular. Observers there see the galactic center higher in the sky, almost directly overhead at certain times of year. The Milky Way dominates the night, a glowing river so bright it casts faint shadows. The Magellanic Clouds, two small satellite galaxies, appear as detached patches of light, companions to the main band. It's a view that northern observers can only dream of, a perspective that reveals the full drama of our galactic home. Every photon you see has been on a journey. The light from nearby stars, those within a few hundred light years, left its source before your grandparents were born, before the Industrial Revolution, before Columbus sailed, before Rome fell. The light from stars across the galaxy, 10,000, 20,000, 30,000 light years away, began its journey before humans existed, before anatomically modern Homo sapiens walked out of Africa. That light traveled through the empty dark for tens of millennia, crossing unimaginable distances, and arrived here, tonight, at the exact moment you happen to look up. There's something profound in that, a connection across space and time that feels almost intimate despite the vast scales involved. The light touching your eyes right now left those stars when the world was a different place, when entirely different dramas were unfolding on Earth, when the configuration of the heavens was subtly altered. And yet, it arrives now, unchanged, carrying information, energy, a message from the past written in photons. The ancient peoples who looked up and saw this band had no idea what they were seeing. They knew it was something significant, something that deserved stories and meaning, but they couldn't have guessed the truth. That it was a galaxy, that they were inside it, that those faint smudges of light represented not clouds or milk or ghosts, but distant suns, each one a furnace of nuclear fusion, each potentially surrounded by worlds of its own. It took until the early 1600s for Galileo to turn his primitive telescope toward the Milky Way and discover that it resolved into individual stars. Countless stars, more than the eye alone could perceive. This was revolutionary, but it still didn't answer the fundamental question of what the Milky Way actually was. For another 3 centuries, astronomers debated. Some thought it was a cloud of glowing gas within a larger cosmos. Others suspected it might be an island universe, a system of stars, separate and distinct, though that idea seemed almost too grand to be believed. The answer didn't come until the 1920s, when Edwin Hubble, using the Mount Wilson Observatory's massive telescope, measured the distances to other spiral nebulae and proved they were galaxies in their own right, millions of light years away. If those were galaxies, separate island universes, then our Milky Way must be one too. We were living inside a galaxy, one among countless others, scattered through the vast expanse of space. That realization changed everything. It expanded the known universe by an almost incomprehensible amount overnight. Suddenly, the cosmos was not just our galactic neighborhood, but an ocean of galaxies, each one containing billions of stars, stretching away in every direction as far as telescopes could see. The Milky Way, once thought to be the entirety of creation, became a single mote in an infinite sea. And yet, despite all we now know, despite our maps and measurements and sophisticated instruments, there's still something irreplaceable about simply looking up, about seeing that river of light with your own eyes, without technology mediating the experience. It connects you to every human who has ever lived and wondered. To the ancient Greeks seeing spilled milk, to the Aboriginal Australians seeing the emu in the sky, to your own ancestors, whoever and wherever they were, looking up from their fires and fields and seeing the same light, asking the same questions, feeling the same awe. So if you haven't seen it, if light pollution has kept it from you, I hope someday you find your way to a dark place, to a sky where the Milky Way reveals itself in full. Because something happens when you see it, a shift in perspective, a recognition of scale. You realize, in a way that no photograph or description can convey, that you are part of something vast, that the universe is not distant and separate, but right there above you, pouring its ancient light onto your upturned face. And in that moment, the galaxy becomes real, not an abstraction, not a concept, but a presence. A home you can see, stretching across the darkness, beautiful and strange and utterly beyond comprehension. From that pale band of light, seen by countless eyes across countless generations, we've learned to map the invisible, to understand what we're part of. And that understanding begins with a story, a history, a long and violent birth written in stars and dust and gravity's patient hand. The Milky Way. You see tonight, that elegant river of light arcing overhead did not spring into existence fully formed. There was no moment of cosmic design, no blueprint drawn by celestial architects. What we observe now, this graceful spiral of stars and gas turning slowly through space, is the product of chaos, of billions of years of collision, consumption, and slow gravitational assembly. The beauty we see is built on wreckage. If you could travel backward through time, rewinding the clock by billions of years, the galaxy would begin to look less and less familiar. The spiral arms would blur, fade, dissolve. The organized disk would thicken, become lumpy, irregular. Go back far enough, perhaps 10 or 12 billion years, and you wouldn't recognize it as a spiral galaxy at all. What you'd see instead would be a chaotic cloud, a loose congregation of gas, dust, and the first primitive stars, all slowly collapsing inward under the pull of gravity. The Milky Way is approximately 13.6 billion years old, nearly as ancient as the universe itself, which began with the Big Bang some 13.8 billion years ago. In cosmic terms, our galaxy formed early, in that wild first epoch when the universe was still young, still hot, still settling into the structures we see today. In the beginning, there were no stars, not yet. The universe after the Big Bang was filled with hydrogen and helium, the simplest elements, forged in the first few minutes of creation. These gases expanded, cooled, and began to clump together under gravity's patient influence. Dark matter, that mysterious invisible substance that we still don't fully understand, provided the scaffolding. Its gravity pulled ordinary matter into denser regions, creating the seeds from which galaxies would grow. Within these collapsing clouds, the very first stars ignited. Astronomers call them population 3 stars, and they were nothing like the stars we see today. They were massive, perhaps 100 times the mass of our sun or more. They contained almost no heavy elements because none had been created yet. They were pure hydrogen and helium, burning with fierce intensity, living fast, and dying young in cataclysmic explosions. When these first giants went supernova, they changed everything. Their deaths seeded the cosmos with new elements: carbon, oxygen, nitrogen, iron, all the building blocks of planets and life, forged in stellar cores and scattered into space by the violence of their final moments. The next generation of stars that formed would be different, enriched, carrying within them the ashes of their predecessors. This is how the Milky Way began, not as a single entity, but as countless small protogalaxies, fragments that would eventually merge together. Gravity drew them toward each other. Some collided violently, their gas clouds slamming together and igniting bursts of new star formation. Others merged more gently, their stars mingling, their orbits intertwining. Over hundreds of millions of years, these fragments coalesced, grew, formed the beginnings of what would become our galaxy. But the Milky Way has never stopped growing. It is still, even now, consuming smaller galaxies, pulling them apart and absorbing their stars. This process, which astronomers call galactic cannibalism, is written into the very structure of the galaxy we see today. If you know where to look, the evidence is everywhere. Consider the stellar streams. These are long, thin ribbons of stars that wrap around the Milky Way like ghostly scarves. They're the remnants of dwarf galaxies that wandered too close and were torn apart by our galaxy's tidal forces. As these smaller systems orbit the Milky Way, our gravity pulls harder on the near side than the far side, stretching them, distorting them, eventually shredding them completely. Their stars are scattered along their orbital path, forming trails that can stretch for hundreds of thousands of light years. The Sagittarius dwarf galaxy is being destroyed right now, in real time, as we speak. It's one of the Milky Way's satellite galaxies, a small elliptical system that made the mistake of passing too close. Over the past few billion years, it's been pulled apart, its stars stripped away and scattered into great looping streams that encircle our galaxy. When astronomers map the positions and velocities of stars in these streams, they can trace the orbit of the original galaxy, reconstructing the path it took as it was slowly dismembered. This isn't ancient history. This is happening now. Stars that once belonged to Sagittarius are now part of the Milky Way's halo, indistinguishable from our native population, except for subtle differences in their chemistry and motion. They orbit in directions that don't quite match the main disk. They move on tilted paths, evidence of their foreign origin. Some even orbit backward, retrograde, circling the galaxy in the opposite direction from the majority of stars. These are the immigrants, the refugees from destroyed worlds, now part of our galactic community. The Sagittarius dwarf is not alone. The Milky Way has consumed dozens, perhaps hundreds, of smaller galaxies over its lifetime. One of the most significant mergers happened about 10 billion years ago, relatively early in the galaxy's history. Astronomers call it the Gaia-Enceladus merger, named after the spacecraft and the mythological giant. A dwarf galaxy, roughly a quarter the mass of the young Milky Way, collided with us, and the impact was profound. This collision didn't just add stars. It fundamentally reshaped the galaxy's structure. The violence of the merger heated the disk, puffing it up, creating what we now call the thick disk, a layer of older stars with more random orbits. Many of the stars in our galactic halo may have come from this ancient collision, scattered outward by the gravitational chaos. When astronomers analyze the chemistry and motion of halo stars, they can identify populations that likely originated in Gaia Enceladus, still carrying the chemical fingerprints of their birth galaxy billions of years after it ceased to exist. There's something haunting about this. The stars we see in the night sky, the ones that form constellations and guide travelers, some of them may not have been born here at all. They may be visitors from lost galaxies, torn from their original homes by forces too vast to resist, now forever part of our own. The Milky Way is not a pristine creation. It's a composite, a mosaic built from the fragments of countless smaller systems, stitched together by gravity over billions of years. And this violence, this consumption, has not been purely destructive. Each merger brought new material, new stars, new gas to fuel future generations of star formation. The heavy elements forged in the cores of stars in those consumed galaxies mixed with our own, enriching the interstellar medium, providing the raw ingredients for planets and eventually life. In a very real sense, we exist because the Milky Way devoured other galaxies. The atoms in your body may have been forged in stars that never belonged to our galaxy, scattered into space when those stars died, mixed into clouds that later collapsed to form our sun and its planets. Over time, as more and more fragments merged, the chaos began to settle. The combined mass started to rotate, and as it rotated, it flattened. This is a natural consequence of angular momentum. A spinning cloud of gas will naturally collapse into a disk, the same way pizza dough flattens when you spin it. The Milky Way's disk formed gradually over the first few billion years as gases settled into a plane and began forming stars in an organized structure. Within this disk, patterns emerged. Spiral arms began to trace themselves through the stars and gas, not as solid structures, but as waves of density, regions where matter bunched up temporarily before dispersing again. These waves, driven by gravitational instabilities and the galaxy's differential rotation, would persist for billions of years, creating the graceful curves we now associate with spiral galaxies. But underneath the elegance, the history of violence remains. The warp in the outer disk, the way it bends upward on one side and downward on the other, is likely caused by gravitational interactions with satellite galaxies. The asymmetries in the spiral arms, the fact that one side of the galaxy appears brighter and more structured than the other, may reflect ancient collisions whose effects still ripple through the disk. Even the central bar, that elongated concentration of stars stretching across the core, may have formed when a massive merger sent shockwaves through the young galaxy, organizing stars into this distinctive structure. Looking at the Milky Way today, with its organized spiral arms and rotating disk, it's easy to forget that this order emerged from disorder, that the graceful structure we see is the product of countless cataclysms, each one reshaping the galaxy, adding complexity, building towards something that appears designed, but is actually the inevitable result of gravity working on matter over unimaginable timescales. And the story isn't over. The Milky Way is still evolving, still consuming, still changing. The Magellanic Clouds, those two small, irregular galaxies visible from the southern hemisphere, are gradually being pulled toward us. In a few billion years, they too will be torn apart and absorbed, their stars joining ours, their gas feeding new generations of star formation. And far beyond, Andromeda approaches, that great spiral twin of our own galaxy, drawing closer by the day, destined to collide with us in about 4.5 billion years in an encounter that will reshape both galaxies completely. So, when you look at that band of light crossing the night sky, remember what you're seeing. Not just stars, but history. Not just structure, but the accumulated result of billions of years of cosmic violence transformed into beauty. The Milky Way is a survivor, built from ruins, assembled from fragments, held together by gravity's patient hand. What appears orderly and calm is, in truth, the settling of ancient chaos, the slow healing of cosmic wounds, the gradual organization of matter into something stable enough, old enough, peaceful enough to allow for planets, life, and quiet moments of wonder beneath a starlit sky. From this violent birth, from this slow assembly of fragments, emerged something remarkable, a structure not random but patterned, organized by forces we're only beginning to understand. Perhaps you've seen pictures of spiral galaxies. Those stunning images captured by the Hubble Space Telescope, galaxies millions of light years away, rendered in exquisite detail, their arms sweeping outward from bright cores in graceful, luminous curves. They look like cosmic pinwheels, like frozen whirlpools of light, perfectly symmetrical, utterly elegant. And when we imagine the Milky Way, we picture ourselves living in something like that, a neat, organized spiral with clearly defined arms spiraling outward in mathematical precision. But here's something that might surprise you. We don't actually know exactly what the Milky Way looks like from the outside. We can't see it that way. We're trapped inside it, embedded in the disk, surrounded by dust and stars in every direction. Mapping the structure of our own galaxy is one of the great challenges of astronomy, like trying to draw a map of a forest while standing in the middle of it with fog all around you. You can see the trees nearby, measure their positions, track their movements. But the overall shape, the pattern of clearings and dense groves, the way the forest spreads across the landscape, all of that has to be inferred, pieced together from incomplete information. For decades, astronomers believed the Milky Way had 4 major spiral arms. Then, newer observations suggested maybe 2, with several smaller spurs branching off. Some models show arms that wrap tightly around the center. Others depict them as loose, fragmentary, barely connected. The truth is, we're still not entirely certain. Current best estimates suggest 2 major arms, Perseus and Scutum Centaurus, and 2 or more minor arms or spurs, including the one we live in, the Orion Spur. But uncertainty aside, there's something far more profound to understand about these spiral arms. Something that changes how you think about galactic structure entirely. The arms are not solid things. They're not fixed structures made of stars, permanently locked together, like the spokes of a wheel. They're patterns, waves, temporary concentrations of matter moving through the disk like ripples across a pond. Think about a traffic jam on a highway. Cars enter the jam from behind, slow down as they move through the congested area, then speed up and exit the front. The traffic jam itself, that region of higher density, moves backward relative to the flow of traffic. It persists as a pattern, even though the individual cars within it are constantly changing. No single car is stuck in the jam forever. They pass through it and emerge on the other side. Spiral arms work the same way. They're density waves, regions where stars, gas, and dust temporarily bunch up as they orbit the galactic center. As matter moves through these denser regions, it slows down slightly, accumulates, increases the local concentration even further. The wave itself rotates around the galaxy, but at a different speed than the stars moving through it. In the inner galaxy, stars orbit faster than the spiral pattern, overtaking it. In the outer regions, stars move more slowly, and the pattern sweeps past them. There's a special radius called the corotation radius, where the orbital speed of stars matches the rotation speed of the spiral pattern. And remarkably, perhaps not coincidentally, we live very close to that radius. This might be important. If you orbit much faster than the spiral pattern, you cross spiral arms frequently, plunging into regions of higher stellar density, increased radiation, more frequent supernovae. If you orbit much slower, the pattern sweeps over you repeatedly, exposing you to similar dangers. But at corotation, you drift along with the pattern, remaining in relatively stable conditions for much longer periods. Some scientists have suggested this could be part of why life emerged on Earth. We've spent billions of years in a relatively calm region of the galaxy, protected not by walls, but by the mathematics of resonance, orbiting in sync with the spiral structure itself. The spiral arms exist because the galactic disk is not uniform. It has regions of slightly higher and lower density, and these regions, once they form, tend to persist and grow. Gravity is self-reinforcing. A region that's slightly denser than its surroundings attracts more matter, which makes it denser still, which attracts even more matter. Over time, these density fluctuations organize themselves into long, sweeping structures that spiral outward from the center, shaped by the rotation of the disk and the distribution of mass within it. As stars and gas pass through these spiral arms, something remarkable happens. The increased density triggers star formation. Gas clouds drifting through the galaxy, cold and diffuse, suddenly find themselves compressed as they enter the denser environment of a spiral arm. This compression can push them past a critical threshold where gravity overwhelms internal pressure and the clouds begin to collapse. Within these collapsing regions, new stars ignite. The most massive of these newborn stars, the hot blue giants, are incredibly luminous but short-lived. They burn through their fuel in just a few million years, a blink of an eye on cosmic timescales. But during their brief lives, they shine with tremendous intensity, pouring out ultraviolet light that ionizes the surrounding gas and makes it glow. These young, bright stars are what make the spiral arms visible. They're like beacons, illuminating the density wave as it moves through the disk. Meanwhile, older stars, the yellow and red suns that make up the bulk of the galaxy's stellar population, exist throughout the disk. They're everywhere, in the arms and in the spaces between. But they're not as luminous, not as dramatically bright as those massive blue giants. So when we look at other spiral galaxies, what we see traced out in light are not all the stars, but specifically the youngest, brightest ones, marking where active star formation is currently happening. The spiral arms glow because they're stellar nurseries, regions where the galaxy is actively making new suns. Threaded through these arms, you'll also find dark lanes, ribbons of shadow cutting across the light. These are dust clouds, vast concentrations of microscopic grains, carbon and silicate and ice scattered through the interstellar medium. Invisible light, dust blocks, and absorbs starlight, creating what appear to be empty voids. But these voids are anything but empty. They're some of the most active regions in the galaxy. Behind those veils of dust, hidden from optical view, stars are being born. Infrared telescopes can peer through the dust, revealing these hidden nurseries in stunning detail. What looks like darkness, invisible light, glows warmly in infrared, heated by newborn stars still wrapped in their birth cocoons. These regions are complex, turbulent, threaded with magnetic fields that shape the flow of gas and guide the collapse of clouds into stars. The dust itself plays a role in this process, helping gas to cool, shielding fragile molecules from destructive radiation, providing surfaces where atoms can meet and combine into more complex forms. The spiral arms are not static. They change, evolve, strengthen, and fade over millions of years. They can split, with a single arm fragmenting into multiple branches. They can merge, with separate structures combining into a single, broader feature. They're influenced by everything around them, by the gravitational pull of the central bar, by passing satellite galaxies, by the distribution of dark matter in the halo. In some galaxies, the spiral pattern is tightly wound, arms curling around the center in multiple loops. In others, the arms are loose and ragged, barely connected at all. The Milky Way appears to fall somewhere in between, with moderately wound arms extending outward in graceful curves. The pitch angle, the measure of how tightly the arms spiral tells astronomers something about the galaxy's mass distribution and rotation. A galaxy with a lot of mass concentrated in its center tends to have tightly wound arms. One with mass more evenly distributed has looser, more open spirals. By studying the pitch angle and comparing it to other measurable properties, we can infer things about the Milky Way's structure that we can't observe directly. Mapping these arms requires multiple techniques. Radio telescopes detect the 21-centimeter emission line of neutral hydrogen, tracing vast clouds of cold gas that extend far beyond the visible disk. This hydrogen often outlines the spiral structure more clearly than stars do, revealing patterns that optical telescopes miss entirely. Infrared observations penetrate the dust, showing where young stars cluster, marking active star-forming regions. Surveys of specific types of stars, like Cepheid variables and young massive giants, help trace the spiral pattern because these stars are associated with recent formation events that happen preferentially in the arms. Magnetic fields also play a role in shaping spiral structure, though their influence is subtle and not yet fully understood. The galaxy's magnetic field threads through the disk, aligned roughly with the spiral arms. This field affects how charged particles move, how cosmic rays propagate, and how gas clouds collapse. In some regions, magnetic pressure can support clouds against gravity, preventing or delaying star formation. In others, it can help channel gas into denser regions, accelerating the process. The interplay between gravity, rotation, magnetic forces, and gas pressure creates a complex, dynamic environment where spiral arms emerge as natural, self-organizing structures. There's something almost hypnotic about the idea of density waves moving through the galaxy, patterns that persist while their constituent parts constantly change. It's reminiscent of waves on the ocean, where water molecules move in circles, but the wave form itself travels across the surface. Or the way a sound wave moves through air, a pattern of compression and rarefaction that propagates while the air molecules themselves simply vibrate in place. The spiral arms are like that, waves of density rippling through the stellar disk, visible only because they trigger star formation that lights them up like foam on a breaking wave. And we, somehow, have ended up orbiting in resonance with these waves, drifting along with the pattern, neither overtaking it nor being overtaken. Our little corner of the Orion Spur has been a relatively stable address for billions of years, long enough for the sun to form, for planets to coalesce, for life to emerge and evolve in the sheltered environment of Earth's surface. The spiral arms have swept past us occasionally, but not so often as to disrupt the delicate processes that led to consciousness, to intelligence, to the capacity to look up and wonder about the very structure we're part of. Perhaps there's something poetic in that. We live in harmony with the galaxy's rhythm, our orbit synchronized with its patterns, not by design, but by the mathematics of motion and the long odds of cosmic chance. And these arms, these graceful curves traced in starlight and shadow, all led somewhere. They sweep inward, converging on a region of gathering density, of increasing light, of concentrated mass and energy. They point toward the heart of the galaxy, toward the luminous core where stars crowd so thickly that the sky itself would blaze. As you journey from our quiet suburban orbit toward the core of the Milky Way, the galaxy changes around you. Slowly at first, then with increasing drama, the spaces between stars shrink. What begins as a gentle increase in stellar density becomes something almost overwhelming. You are approaching the galactic bulge, the luminous heart of our galaxy. And the closer you get, the more the fundamental character of space itself seems to shift. Out here, where we live, 26,000 light-years from the center, the nearest star to our sun is Proxima Centauri, more than 4 light-years away. 4 years of travel at the speed of light just to reach the closest neighboring sun. The space between stars in our region feels vast, empty, dominated by darkness, punctuated by distant points of light. This is normal for the galactic suburbs. This is what most of the disk looks like, stars scattered like islands in a dark sea. But move inward, closer to the core, and those distances collapse. At 10,000 light-years from the center, stars might be separated by just a light-year or two. Closer still, measured in light months. In the densest regions of the bulge, stars can pass within light weeks or even light days of each other. Imagine a sky where neighboring stars are not faint dots, but brilliant points of light, bright enough to cast shadows at night, where the darkness between sunset and sunrise never truly arrives because the combined glow of nearby suns keeps the sky in perpetual twilight. This is the environment of the galactic center, a place so different from our own that it challenges the imagination. If Earth somehow found itself transplanted there, our night sky would be unrecognizable. Thousands of stars would be visible even in daylight. The brightest ones would be brighter than Venus appears to us, hanging in the sky like luminous jewels. The combined light of all those nearby suns would flood the surface with a soft, perpetual glow. Darkness, true darkness, might never come. The bulge itself is not a simple sphere. When astronomers mapped it carefully using infrared observations that can penetrate the obscuring dust, they discovered something unexpected. The central region has a strange, elongated shape, often described as peanut-like or resembling an X when viewed edge-on. This structure extends roughly 10,000 light-years from end to end, puffed up above and below the galactic plane like a three-dimensional hourglass made of stars. This peanut shape is thought to be a consequence of the central bar, that elongated concentration of stars stretching across the core. Bars form naturally in many spiral galaxies through gravitational instabilities in the rotating disk. Over time, as stars orbit the center, their collective gravity can organize them into an elongated structure, a bridge of stars crossing the middle of the galaxy. The Milky Way's bar is approximately 27,000 light-years long, rotating slowly, taking about 100 million years to complete one full turn. But bars are not rigid. They're made of stars in motion, orbiting on complex paths shaped by the combined gravity of all the mass around them. Some stars orbit in the plane of the disk. Others follow elongated elliptical paths that take them high above the plane and back down below it. When enough stars move on these vertical orbits, the bar appears to buckle, creating that characteristic peanut or X shape. It's a purely gravitational sculpture, matter organizing itself into form through nothing but motion and mutual attraction. The bar's influence extends throughout the inner galaxy. Its gravity shapes the spiral arms, determining where they attach to the bulge and how tightly they wind. It funnels gas inward, channeling material from the outer disk toward the center, feeding star formation in the bulge and providing fuel for the supermassive black hole at the very core. The bar acts like a cosmic conveyor belt, redistributing matter, stirring the inner galaxy, keeping it dynamically active despite its age. The stars in the bulge are predominantly old, ancient red and yellow giants, stars that formed when the galaxy was young, more than 10 billion years ago. They've long since exhausted the hydrogen in their cores and expanded into the giant phase of their evolution. Their light is soft, golden, the color of aged starlight. When you look at the bulge in infrared images, where dust doesn't block the view, it glows with this warm, amber hue, a concentration of ancient suns gathered at the galaxy's heart. But alongside these ancient stars, surprisingly, you also find some of the youngest, most massive stars in the entire galaxy. Near the very center, within just a few light years of the supermassive black hole, astronomers have discovered clusters of enormous blue giants, stars dozens of times more massive than the Sun, burning with ferocious intensity. These stars are young, just a few million years old at most, and their presence in such a hostile environment is something of a puzzle. How did they form there? The tidal forces near the black hole should shred gas clouds before they can collapse into stars. The radiation environment is harsh, flooded with X-rays and gamma rays from the black hole's surroundings. Yet somehow, star formation happened. Perhaps gas was funneled inward by the bar, compressed and shocked until it reached densities high enough to overcome the disruptive tidal forces. Perhaps these stars formed elsewhere and migrated inward, though that seems unlikely given how quickly they would be disrupted. It remains an open question, a mystery at the heart of the galaxy. The center is a region of extremes. Supernovae explode more frequently there because of the high stellar density. When massive stars die, they release tremendous amounts of energy, enriching the surrounding gas with heavy elements and triggering shock waves that ripple through the interstellar medium. Cosmic rays, high-energy particles accelerated to near light speed by supernova remnants and other violent processes, stream through the region in higher concentrations than anywhere else in the galaxy. Radiation levels are intense. X-ray emissions from close binary systems, where a compact stellar remnant, a white dwarf or neutron star, strips matter from a companion star, create bright X-ray sources scattered throughout the bulge. The black hole itself, when it captures and heats infalling material, can flare dramatically in X-rays, briefly illuminating the galactic center before fading back to relative quiescence. Any planet orbiting in this environment would face challenges we can barely imagine. The radiation alone would make surface life difficult, requiring either thick atmospheres or subsurface habitats. The frequent supernovae could strip away atmospheric layers or even sterilize the surface with bursts of gamma rays. And the sheer crowding of stars means gravitational interactions would be common. A close pass by another star could perturb a planet's orbit, sending it spiraling inward toward its sun, or ejecting it entirely into interstellar space. And yet, despite these dangers, the center is also incredibly rich. Heavy elements, those building blocks necessary for rocky planets and complex chemistry, are abundant. The gas has been enriched by countless generations of stars that lived, died, and returned their processed contents to the interstellar medium. If planets can form and survive in such an environment, they would have access to a chemical palette far richer than what was available to the early solar system when it formed. The innermost few thousand light years are sometimes called the central molecular zone, a region containing enormous clouds of molecular gas, enough raw material to form millions of new stars. These clouds are dense, turbulent, threaded with magnetic fields, and stirred by stellar winds. Star formation does occur here, but it's suppressed compared to what you'd expect given the amount of gas present. Something about the environment, perhaps the strong magnetic fields or the intense radiation, makes it harder for clouds to collapse. Surrounding the central molecular zone and scattered throughout the bulge are massive star clusters, dense congregations of stars bound together by their mutual gravity. The Arches cluster and the Quintuplet cluster are two of the most prominent examples, each containing hundreds of extremely massive stars packed into a region just a few light years across. These clusters are young, just a few million years old, but their location near the galactic center means they're experiencing extreme tidal forces that will eventually tear them apart. They're bright, dramatic, but temporary features in the bulge's stellar population. All of this, the ancient stars, the young massive clusters, the dense gas, the radiation, the magnetic fields, all of it is organized around and influenced by a single dominant feature. At the absolute center of the galaxy, within a region smaller than our solar system, lies an object of almost incomprehensible mass and density. We cannot see it directly. Dust blocks our view in visible light, but its influence is undeniable, written in the motion of everything around it. Stars near the galactic center don't orbit slowly, sedately, the way stars do out here in the suburbs. They whip around at tremendous speeds, thousands of kilometers per second, tracing tight elliptical paths that bring them screaming close to the center before flinging them back outward. Astronomers have tracked some of these stars, designated with names like S2 and S0102, watching them complete full orbits in just a few decades. One star, S2, orbits the center every 16 years, reaching speeds of up to 5,000 kilometers per second at its closest approach. What could cause such extreme velocities? Only one thing: an enormous concentration of mass in an incredibly small space. By measuring the orbits of these stars with exquisite precision, astronomers have calculated that the object at the center must contain approximately 4 million times the mass of our Sun, and it must occupy a region no larger than a few light hours across, smaller than the diameter of Pluto's orbit. There is only one object in the known universe that fits this description: a supermassive black hole. We call it Sagittarius A star, named after the constellation where it resides and marked with an asterisk to distinguish it from other radio sources in the region. It is the gravitational anchor of the Milky Way, the point around which all those hundreds of billions of stars ultimately orbit. It is the dark heart of the galaxy, invisible yet undeniable, silent yet overwhelming in its influence. Radio telescopes detect a compact source of emission from its location, radiation produced by the small amount of matter currently falling toward it. Occasionally, infrared flares light up as gas and dust are heated to tremendous temperatures in the black hole's immediate vicinity before crossing the event horizon and vanishing forever. X-ray observatories catch glimpses of high-energy emissions when particularly dramatic infall events occur. But most of the time, Sagittarius star is quiet, dormant, far less active than the supermassive black holes in many other galaxies, some of which blaze as quasars, outshining their entire host galaxies with the energy released by infalling matter. Our black hole seems to be sleeping, consuming only a trickle of material, generating only faint whispers of radiation compared to what it could produce if it were actively feeding. This wasn't always the case. Evidence suggests that in the past, perhaps just a few million years ago, Sagittarius, a star, was far more active. The giant gamma-ray bubbles extending above and below the galactic plane, discovered by the Fermi telescope and stretching for tens of thousands of light years, may be the remnants of an ancient outburst from the black hole. If so, the center once blazed like a quasar, visible across intergalactic distances, before settling back into its current quiescence. The environment immediately around the black hole is one of the most extreme in the galaxy. Space-time itself is warped by the immense gravity. Time runs more slowly there compared to out here in the suburbs, a consequence of general relativity. Matter orbiting close to the event horizon moves at substantial fractions of light speed, caught in the grip of gravity so strong that nothing, not even light, can escape if it crosses that final boundary. And yet, even in this maelstrom of gravity and radiation, stars orbit and survive. They've been shaped by the environment, their outer layers perhaps stripped away by tidal forces or stellar collisions. But they endure, tracing their wild paths around the invisible center, marking the location of something we cannot see, but whose reality is written in their motion, undeniable and profound. How massive is it? Approximately 4 million times the mass of our sun. 4 million suns worth of matter, compressed into a region so small that if you could somehow approach it, you would find its event horizon. That point of no return spans only about 24 million kilometers across. That sounds large, perhaps, until you realize it's barely larger than the distance between the Sun and Mercury. 4 million stellar masses concentrated into a space that could fit comfortably inside our inner solar system. The density is beyond comprehension, beyond any material we know. At the center, according to Einstein's equations, lies a singularity, a point of zero volume and infinite density where the laws of physics, as we understand them, break down completely. We cannot see this directly. The event horizon emits no light. By definition, nothing that crosses that boundary can ever return. Not matter, not energy, not even information. Light itself, trapped by the immense gravity, spirals inward and vanishes. If you could somehow hover just outside the event horizon and shine a flashlight outward, the light would curve back, unable to escape, falling into the darkness behind you. But we can see its effects. Oh, can we see its effects? Stars near the galactic center move in ways that are impossible to explain without something enormously massive at the center. Beginning in the 1980s, astronomers began tracking individual stars orbiting the galactic core, measuring their positions with increasing precision year after year. One star, in particular, designated S2, became the key to understanding what lurked at the center. S2 is a blue giant, bright and massive, but that's not what makes it remarkable. What makes it extraordinary is its orbit. It circles Sagittarius A star in just 16 years, completing a full ellipse faster than it takes Pluto to orbit our Sun once. At its closest approach, it reaches speeds of more than 5,000 kilometers per second, nearly 2% of the speed of light, screaming around the invisible center before being flung back outward on its long elliptical path. Watching S2 orbit is like watching a cosmic clock. Each time it swings close to the black hole, instruments measure its position and velocity with exquisite precision. By applying Kepler's laws of orbital motion, the same laws that govern planets around stars, astronomers can calculate the mass of the object S2 orbits. The answer is always the same: 4 million solar masses. And the space it occupies is vanishingly small. There is only one object in the known universe that fits these parameters: a supermassive black hole. Other stars join this dance. S0102 orbits even faster, completing its circuit in just over 11 years. Dozens of stars have been tracked, each one tracing an ellipse around the same invisible point, each one confirming through its motion that something massive and compact dominates the galactic center. Together, these stars form a kind of cosmic ballet, choreographed by gravity, moving with precision around a conductor they cannot see. The event horizon itself is a boundary in space-time, not a physical surface. If you fell toward it, you wouldn't encounter a wall or barrier. You would simply reach a point where escape becomes impossible. From an outside observer's perspective, you would appear to slow down as you approached, your light redshifting, your clock running slower and slower relative to theirs due to time dilation. Eventually, you would seem to freeze at the horizon, your image fading and reddening until it disappeared into the darkness. But from your own perspective, assuming you somehow survived the tidal forces, you would cross the horizon in finite time, falling inward, unable to turn back, unable even to perceive that you'd crossed a point of no return. Inside the event horizon, space-time is so warped that all paths lead inward. There is no direction you could travel, no thrust you could apply that would take you back outward. The future direction of space-time itself points toward the singularity at the center, and you would fall toward it as inevitably as you fall forward through time. The journey from horizon to singularity would take only fractions of a second for a black hole of this mass. And then, well, then the equations break down. We don't know what happens at a singularity. Our physics cannot describe it. But most matter never crosses the horizon. It orbits, circles, heats up through friction and compression as it spirals inward. This creates an accretion disk, a flat spinning structure of gas and dust that glows from the energy released as gravitational potential energy converts to heat. In many galaxies, these accretion disks are enormous, bright, active, feeding the black hole massive amounts of material and releasing energy that outshines the entire galaxy. These are quasars, active galactic nuclei, beacons visible across billions of light years. Sagittarius A star is not like that. It is quiet, almost dormant. Its accretion disk is sparse, thin, barely visible. The black hole consumes matter at a trickle, perhaps the equivalent of only a few Earth masses per century. This is puzzling. There is abundant gas in the central molecular zone surrounding it. Stars orbit nearby, shedding material through stellar winds. Why doesn't more fall in? The answer seems to involve magnetic fields and the complex dynamics of gas near the event horizon. Much of the material that spirals inward is heated to such high temperatures that it generates pressure, radiation, and outflows that actually blow matter back outward before it can cross the horizon. The black hole, ironically, is so efficient at converting gravitational energy to heat that it prevents much of its potential fuel from reaching it. It is, in a sense, regulating its own feeding rate. Still, it does feed. Occasionally, perhaps when a particularly dense clump of gas or a passing star ventures too close, Sagittarius A star flares. Infrared telescopes catch these events, sudden brightenings that last for hours before fading back to quiescence. X-ray observatories detect similar flares, brief, intense pulses of high-energy radiation. These are moments when matter falls inward in larger amounts than usual, heated to millions of degrees before vanishing across the horizon. Radio telescopes detect a persistent glow from the region. Synchrotron radiation produced by electrons spiraling in magnetic fields near the black hole. This radiation allowed astronomers to pinpoint Sagittarius A star's location with incredible precision, mapping a compact source at the exact center where all those orbiting stars converge. And then, in 2022, something extraordinary happened. The Event Horizon Telescope, a global network of radio dishes coordinated to work as a single Earth-sized instrument, released an image of Sagittarius A star. Not of the black hole itself, which emits no light, but of its shadow, the dark silhouette it casts against the glowing accretion disk behind it. The image showed a ring of light, orange and yellow, with a dark center. That darkness is the black hole's shadow, slightly larger than the event horizon itself due to gravitational lensing, the bending of light around the massive object. Creating this image required coordinating telescopes across the planet, from Chile to Hawaii to the South Pole, synchronizing their observations to nanosecond precision, and then processing petabytes of data to reconstruct what the black hole's environment looks like. The result was stunning, not just for its beauty, but for what it confirmed. The size and shape of the shadow matched predictions from general relativity with remarkable accuracy. Einstein's century-old equations, tested in the most extreme environment imaginable, passed with flying colors. Sagittarius A star is smaller and more variable than the only other black hole ever imaged, M87 star, which sits at the center of a galaxy 55 million light-years away. 7 star is thousands of times more massive and correspondingly larger. But our black hole being so much closer, spans a similar angular size in the sky, making it just barely possible to resolve with current technology. The variability comes from its sparse accretion disk. Matter orbits and falls in on timescales of minutes to hours, causing the appearance to flicker and change. This made imaging it more challenging than M87 star, whose disk changes more slowly. Near the event horizon, strange things happen to space-time itself. Time dilation becomes extreme. A clock hovering just outside the horizon would tick much more slowly than one far away. If you could watch someone falling toward a black hole, they would appear to move in slow motion, their clock running slower and slower as they approach the point of no return. This isn't an illusion or a trick of observation. Time genuinely runs at different rates in different gravitational fields, a consequence of general relativity that has been measured and confirmed in laboratories and with GPS satellites. There is a region outside the event horizon called the photon sphere, where light can orbit the black hole in circular paths. At this radius, a beam of light shot tangentially would circle forever, neither falling in nor escaping. It's an unstable orbit. Any slight perturbation would send the light spiraling inward or outward, but mathematically, it exists. For Sagittarius A star, this photon sphere lies about 1.5 times farther from the center than the event horizon itself. The tidal forces near the black hole are immense. If you fell in feet first, the gravity pulling on your feet would be so much stronger than the gravity pulling on your head that you would be stretched vertically and compressed horizontally. Physicists call this spaghettification, a term that sounds whimsical but describes a genuinely horrifying process. For Sagittarius A star, these tidal forces become lethal well before you reach the event horizon. You would be torn apart, atomized, your constituent particles spiraling inward separately. How did this black hole form? We're not entirely certain. One possibility is that it grew from a stellar mass black hole, the remnant of a massive star, which accreted material over billions of years, growing slowly from perhaps 10 or 100 solar masses to 4 million. But the timescales seem problematic. Could it really grow that much in the age of the universe? Especially given how little it's consuming now? Another possibility is direct collapse. In the early universe, perhaps a massive cloud of gas collapsed directly into a black hole without ever forming a star first, creating a seed black hole of thousands or even hundreds of thousands of solar masses. This seed could then grow more easily to the supermassive scale we observe today. Evidence for which scenario actually occurred is scarce, buried in the distant past and hidden behind the dust that shrouds the galactic center. What's certain is that Sagittarius A star has profoundly influenced the galaxy's evolution. Its gravity anchors the entire structure. 200 billion stars orbit this central point, their paths determined by its mass and the distribution of matter around it. During more active phases in the past, when it fed more aggressively, it would have produced powerful outflows and radiation that influenced star formation throughout the inner galaxy, heating gas, driving winds, perhaps regulating how quickly the galaxy could form stars. Evidence suggests it was more active in the recent past, perhaps just a few million years ago. Those giant gamma-ray bubbles extending tens of thousands of light years above and below the galactic plane, discovered by the Fermi telescope, may be the remnants of an ancient outburst when Sagittarius A star consumed a large amount of material in a brief feeding frenzy. If so, the center once blazed far brighter than it does today, perhaps even glowing as a modest quasar, visible to observers in nearby galaxies. Going back billions of years, in the galaxy's youth, it likely was a quasar, actively accreting, shining brightly, shaping the formation of the disk and bulge through its feedback. Most galaxies went through such phases before settling into their current quieter states. There are mysteries here that physics has not yet solved. What happens to information that falls into a black hole? According to quantum mechanics, information cannot be destroyed, yet anything crossing the event horizon seems to disappear completely. This apparent contradiction, called the information paradox, has puzzled physicists for decades. Stephen Hawking's theoretical work on black hole radiation, suggesting that black holes slowly evaporate over unimaginably long timescales, may provide part of the answer, but the details remain contentious and unresolved. For Sagittarius A star, such evaporation is purely theoretical and impossibly slow. It would take vastly longer than the current age of the universe for a black hole of this mass to evaporate significantly through Hawking radiation. For all practical purposes, it is eternal. And yet, it is not destroying the galaxy. Despite the immense gravity, despite the inescapable pull, once you cross the horizon, the black hole only dominates a tiny region at the absolute center. Beyond a few light years, its gravity is no stronger than an equivalent mass of ordinary matter would be. It holds the galaxy together, not through some exotic force, but simply through its mass, the same gravitational force that governs planets orbiting stars. It is, in its way, a conductor, not producing sound, not creating the motion, but organizing it, providing the central reference point around which everything else arranges itself. The 400 billion stars of the Milky Way move in response to the combined gravity of all mass in the galaxy. But at the center of that distribution sits this silent, invisible object, marking the point of deepest gravitational potential, the bottom of the well around which everything else spirals. And so it waits, patient and eternal, consuming the occasional wisp of gas, occasionally flaring as matter heats and radiates before vanishing across the horizon, but mostly silent, mostly dark, mostly still. A point of darkness at the heart of light, a mystery at the center of our cosmic home, reminding us that even at the galaxy's core, there are boundaries beyond which our understanding fades into shadow. Pull back now from that dark center, that point where physics bends and breaks, and return to our own motion through the galaxy. We've peered into the heart, glimpsed the invisible conductor, but now it's time to follow the path we're actually traveling. Because while Sagittarius A star sits motionless at the gravitational center, everything else, ourselves included, is on a journey, a long, looping pilgrimage around that central point that has been continuing since before the Earth existed and will continue long after the sun dies. 828,000 kilometers per hour. That's how fast our solar system moves through the galaxy. 230 kilometers every single second, fast enough to circle the Earth's equator in less than 3 minutes. And yet, sitting here, you feel nothing. No wind, no acceleration, no sense whatsoever of this tremendous velocity. The motion is so smooth, so constant, that it becomes invisible. Like a passenger on a ship sailing calm seas, you have no direct perception of the movement. Everything around you, Earth, Moon, planets, moves together in concert, and so the velocity disappears into a kind of stillness. But the journey is real. The sun, pulling its family of planets along like a ship trailing boats behind it, sweeps through the Milky Way on a path that takes approximately 225 to 250 million years to complete. Astronomers call this a galactic year, a unit of time so vast that it redefines patience, so immense that recorded human history occupies less than 1/10,000th of a single orbit. Think about that for a moment. All of civilization, from the first cities of Mesopotamia to the present day, represents a tiny arc in the sun's current circuit around the galaxy, barely a few hundredths of a degree in a 360-degree journey. In all of its 4.6 billion years of existence, our sun has completed only about 20 orbits, 20 times around. 20 great sweeping loops through the spiral structure of the galaxy, rising through spiral arms and drifting through the quiet lanes between them. It's a small number, remarkably small for something so ancient. If you lived for 70 years and took a walk around your neighborhood every day, you'd complete more than 25,000 circuits. The sun, in nearly 5 billion years, has managed only 20 trips around its much vaster neighborhood. This orbit is not a perfect circle. It's slightly elliptical, stretched, and more than that, it's three-dimensional. As we orbit the galactic center, we also bob gently up and down through the galactic plane, rising above it, then sinking below in a slow vertical oscillation. Imagine the orbit as a gentle wave drawn in 3 dimensions, a sinuous path that crosses the flat plane of the disk every 30 million years or so. Right now, we're moving upward, rising above the midplane, currently about 70 light-years above it, and still climbing. In about 15 million years, we'll reach maximum height, perhaps 230 light-years above the plane, before gravity pulls us back down. This vertical motion is driven by the gravitational pull of all the mass in the galactic disk. As we rise above the plane, the disk's gravity pulls us back toward it. We fall back down, overshoot, dip below, and then get pulled back up again, oscillating like a weight on a spring. Though the spring here is not metal coiled, but gravitational potential energy stretched across light years. Some researchers have wondered whether these crossings of the galactic plane might correlate with events on Earth. When we pass through the denser midplane region, we're exposed to more dust, more cosmic rays, potentially more gravitational perturbations from passing molecular clouds or nearby stars. Could this trigger comet showers from the distant Oort cloud, sending icy bodies plunging toward the inner solar system, where some might impact Earth? Could increased cosmic ray exposure affect Earth's climate, perhaps seeding cloud formation or influencing atmospheric chemistry? There have been attempts to link our vertical oscillations to mass extinction events in Earth's fossil record. The data is suggestive, but far from conclusive. Extinctions happen for many reasons, and teasing out a subtle galactic signal from the noise of volcanism, asteroid impacts, climate shifts, and other terrestrial factors is extraordinarily difficult. Still, the idea is tantalizing that our journey through the galaxy might have, in subtle ways, shaped the story of life on our world. What was Earth like the last time we were at this point in our orbit? 225 million years ago, the world looked nothing like it does today. There were no humans, no mammals scurrying through underbrush, no birds in the sky. The continents were fused together into a single massive landmass called Pangaea, and the climate was harsh, hot, and arid across much of the interior. At the ocean's edges, in scattered forests, the first dinosaurs were just beginning to appear, small bipedal creatures that would, over the coming tens of millions of years, diversify into the giants that would dominate the Mesozoic. The stars overhead would have been different too. Not dramatically, most stars move relatively slowly compared to the vast scale of the galaxy, but subtly. Constellations would have been slightly different shapes. Some stars that are now nearby would have been distant. Others, now far away, would have been part of our neighborhood. The sun passes different neighbors on each orbit, like a commuter taking the same train route but encountering different passengers each journey. Go back another orbit, 450 million years ago, and Earth was even more alien. Life was only beginning its tentative exploration of the land. The continents were barren rock and sand. In the oceans, fish dominated, but amphibians had not yet evolved. Plants were just starting to colonize the margins of continents, turning stone into soil through their slow chemical weathering and the decay of their organic matter. The sun orbited through a galaxy that had never seen forests, never heard wind rushing through leaves, never known footsteps on solid ground. 3 galactic years ago, roughly 675 million years in Earth's past, the planet was emerging from a possible snowball Earth event. Its surface perhaps entirely frozen, ice extending from pole to pole, life persisting only in the oceans beneath the ice or near volcanic vents. The sun was younger then, its luminosity slightly lower, its path through the galaxy, carrying it through regions we'll never visit again, past stars that have since moved to other parts of the disk. These deep time scales, these galactic years, put human existence into a perspective that can feel either humbling or overwhelming. All of human history, every empire that rose and fell, every war fought, every discovery made, every life lived, all of it happened during one tiny segment of the sun's current orbit. We are recent arrivals in a journey that began long before us and will continue long after we're gone. As the sun orbits, it doesn't travel alone. It was born with siblings, hundreds or perhaps thousands of other stars that form from the same collapsing molecular cloud 4.6 billion years ago. That birth cluster would have been a spectacular sight, a dense congregation of newborn stars, some massive and brilliant, others small and dim, all drifting together through the galaxy. But over time, gravitational interactions, encounters with other clusters, and the simple differential rotation of the galaxy scattered those siblings. Within a few 100 million years, the cluster would have dissolved completely, its members flung across different orbits, now indistinguishable from the background stellar population. Those sibling stars are still out there, somewhere. Astronomers have searched for them, looking for stars with the same age, same chemical composition, same birth signature as our Sun. A few candidates have been identified, stars that might have shared our origin, born from the same cloud, witnesses to the same ancient dawn. But most are lost, scattered across such vast distances that we'll likely never identify them all. They're family in a cosmic sense, but family we'll never know. The stellar neighborhood around us is constantly changing. Stars that are close now will drift away. Others, currently distant, will approach. In 30,000 years, the star Vega will be closer to us than Proxima Centauri is today. In 100,000 years, our night sky will be noticeably different. Familiar constellations warped into new configurations. This is the nature of motion in the galaxy. Nothing is fixed. Everything drifts. Even our sense of what's nearby is temporary, a snapshot of relationships that shift over millennia. Our motion through the galaxy also means we pass through different environments over time. Right now, we're inside a low-density region called the local bubble, a cavity carved out by ancient supernovae that exploded several million years ago, blowing away most of the gas in a region spanning hundreds of light years. The interstellar medium here is thin, hot, ionized. This has consequences for the heliosphere, the protective bubble of charged particles the Sun creates around the solar system. In low-density regions, the heliosphere can expand farther. In denser regions, it compresses. In about 10 to 20,000 years, we'll exit the local bubble and enter a denser region of the interstellar medium. When that happens, the heliosphere will shrink, compressed by the increased external pressure. This could allow more cosmic rays and interstellar particles to penetrate into the inner solar system. Some researchers have speculated this might influence Earth's climate or even affect cloud formation patterns in our atmosphere. Again, the evidence is suggestive, but not conclusive. These are subtle effects, difficult to detect or predict with certainty. As we orbit, we occasionally pass through spiral arms, plunging into regions of higher stellar density, more active star formation, and increased supernova rates. These crossings don't happen frequently because, as mentioned earlier, we orbit near the corotation radius, where our speed roughly matches the spiral pattern's rotation. But over many orbits, we do drift in and out of arms. Some studies have attempted to correlate arm crossings with extinction events on Earth, proposing that increased supernova activity during these periods could bombard Earth with radiation or trigger climate changes. The idea is controversial, and the correlation's weak, but it illustrates how our galactic journey might, in subtle ways, influence conditions on our world. The Sun is not orbiting in isolation either. It's part of the larger motion of all stars in its region, drifting together in loose associations called moving groups. These are stars that share similar velocities and ages, born from the same general region of the galaxy and still moving together through space. Our sun has a peculiar velocity relative to the average motion of nearby stars, moving at about 13 kilometers per second in a direction toward the constellation Hercules. Astronomers call this direction the solar apex, the point in the sky we're heading toward. Meanwhile, the point we're moving away from in the opposite direction is called the solar antipex. As the sun plows through the interstellar medium, the heliosphere creates a bow shock, similar to the wake a boat leaves in water, or the shock wave a supersonic jet creates in air. This bow shock has been detected and mapped, a subtle signature of our motion through space, the boundary where the solar wind meets and pushes against the tenuous gas between stars. The long-term future of our orbit is, in most respects, stable. Gravitational simulations suggest the sun will continue on, roughly its current path, for billions of years to come. Small perturbations might occur if we pass unusually close to a massive molecular cloud or experience a close encounter with another star, but such events are rare. The galaxy is vast, and despite containing hundreds of billions of stars, the space between them is so large that collisions or near misses are extraordinarily uncommon. The sun will die before it completes many more orbits. In about 5 billion years, it will exhaust the hydrogen in its core and begin its evolution into a red giant, swelling to perhaps 100 times its current diameter, possibly engulfing Earth in the process. When this happens, the sun will have completed roughly 22 or 23 galactic orbits, just a few more than it's managed already. It will never see 25 orbits. Its lifespan, though vast by human standards, is limited even on galactic timescales. But the journey itself will continue. After the sun sheds its outer layers as a planetary nebula, its core will remain as a white dwarf, a cooling ember that will continue orbiting the galaxy for trillions of years, slowly fading, eventually becoming a black dwarf, a cold, dark cinder drifting through space, invisible but still bound by gravity to the galactic dance. The atoms that once made up Earth, scattered by the sun's death throes, will mix into the interstellar medium, eventually incorporated into new stars, new worlds. The matter persists. The journey continues, just in different forms. There's something both humbling and comforting in understanding this motion. We are not still. We are not fixed. We are travelers, moving through space and time on a path that connects us to the deep past and the far future. Every moment you exist, you're racing through the galaxy at speeds that would make any earthly vehicle seem laughably slow. And yet this motion is gentle, patient, a rhythm that has continued for eons and will continue for eons more. Our orbit carries us through a galaxy that is still, even now, creating. 13 billion years after its formation, the Milky Way has not finished making stars. The process continues, slower than in its youth perhaps, less frantic than during the violent merger epochs of the distant past, but ongoing nonetheless. And as we sweep through the spiral arms on our long galactic journey, we pass through the very regions where this creation happens. stellar nurseries, cosmic cradles, places where gravity, given enough time and the right conditions, transforms diffuse clouds of gas into concentrated spheres of nuclear fire. These nurseries exist throughout the galaxy, scattered along the spiral arms where gas is compressed and star formation triggered. Some are nearby, close enough that even amateur telescopes can reveal their glowing structures. The Orion Nebula, perhaps the most famous, hangs in the night sky as a fuzzy patch just below Orion's belt, visible to the naked eye as a soft smudge but revealed through binoculars as a luminous cloud, and through larger telescopes as an impossibly complex tapestry of gas, dust, and newborn stars. It lies roughly 1,350 light-years away, making it one of the closest major star-forming regions to Earth, close enough that we can study it in exquisite detail, watching star formation happen in something approaching real time. The raw material for stars is the interstellar medium, that thin gas that fills the spaces between existing stars. Most of it is hydrogen, the simplest and most abundant element in the universe. But there's also helium and trace amounts of heavier elements, everything from carbon to oxygen to iron. All the products of previous generations of stars that lived, died, and scattered their enriched contents into space. This material isn't distributed evenly. It clumps, concentrates, forms clouds, some small and others truly enormous. Giant molecular clouds, as astronomers call them, are the largest structures in the galaxy's interstellar medium. They can span hundreds of light years across and contain enough mass to form millions of stars. These clouds are cold, typically just 10 to 20 degrees above absolute zero, and incredibly dark. The hydrogen within them exists not as individual atoms, but as molecules, H2, two hydrogen atoms bonded together. Mixed with this molecular hydrogen is dust, microscopic grains of carbon, silicates, and ice. Particles so tiny that trillions would fit on the head of a pin, but so numerous that collectively they block visible light almost entirely. In visible wavelengths, these clouds appear as dark patches against the background stars, regions of shadow, seemingly empty voids. But they're anything but empty. Peer at them with infrared telescopes or radio dishes, and they light up with structure, glowing faintly from the warmth of dust particles, emitting radio waves at specific frequencies corresponding to molecular transitions. These observations reveal the cloud's true nature as dense, turbulent, magnetically threaded environments where chemistry happens, where molecules more complex than hydrogen form and drift through the darkness. For most of a cloud's existence, it simply drifts. Gravity pulls inward, trying to compress it. But internal pressure, turbulence, and magnetic fields resist. The cloud remains in a kind of balance, neither collapsing nor dispersing, just existing as a cold, dark reservoir of potential. But occasionally, something tips the balance. A nearby supernova's shockwave slams into the cloud, compressing part of it. Or the cloud passes through a spiral arm, where the increased density of the galactic environment squeezes it from outside. Or two clouds collide, their combined mass overwhelming the forces that resist collapse. When this happens, when gravity finally overcomes the internal support, the cloud begins to fall inward. Not all at once, but in regions, in fragments, in countless separate cores scattered throughout the larger structure. This is why stars form in clusters, not in isolation. One collapsing cloud produces hundreds or thousands of stars, all born from the same parent material, all emerging together in a relatively short span of cosmic time. As each core collapses, it heats up. Gravitational potential energy, the energy stored in the separated mass of the diffuse cloud, converts to thermal energy as particles fall inward and collide with increasing frequency. The center grows denser, hotter, more concentrated. Material continues to rain in from the surrounding envelope, building up the central mass grain by grain, atom by atom. This is a protostar, not yet generating energy through fusion, but glowing nonetheless from the heat of its own contraction. The collapsing material carries angular momentum, that property of rotation that cannot be destroyed, only redistributed. As the cloud shrinks, conservation of angular momentum forces it to spin faster, like an ice skater pulling in their arms. But not everything can fall directly to the center. Material with too much angular momentum flattens into a disk, a spinning plane of gas and dust surrounding the growing protostar. This is a protoplanetary disk, and within it, planets will eventually form through the slow accumulation of dust into pebbles, pebbles into rocks, rocks into planetesimals, planetesimals into worlds. The protostar continues to grow, fed by material from the disk and the remaining envelope. When its core reaches temperatures around 10 million degrees, something extraordinary happens. Hydrogen nuclei, normally repelling each other through electromagnetic force, are moving so fast, so energetically, that they overcome this repulsion and fuse together, forming helium. This fusion releases energy, tremendous amounts of energy, and that energy generates pressure that pushes outward, finally halting the collapse. The protostar stabilizes, gravity pulling in, radiation pressure pushing out, the two forces reaching equilibrium. A star is born. This process takes time. From the initial collapse to the ignition of fusion might span 1 million years for a sun-like star, longer for smaller stars, shorter for massive ones. During this time, the young star goes through various phases, some violent and active. The T Tauri phase, named after the first star of this type discovered, is characterized by powerful stellar winds and irregular brightness. The newborn star is clearing out its surroundings, blowing away the remaining gas and dust, gradually revealing itself. Jets of material shoot out from the poles, narrow beams of gas accelerated to hundreds of kilometers per second, extending for light years into space. These jets are visible in many stellar nurseries, glowing threads pointing away from embedded protostars. The most massive stars, those more than 20 or 30 times the sun's mass, form differently. They're so luminous, even before fully forming, that their radiation pressure pushes against infalling material, resisting further accretion. How they manage to gather enough mass to become the giants we observe remains somewhat mysterious. Perhaps material falls in through the disk, rather than directly, or perhaps They form through the merger of smaller protostars. The details are still being worked out through observations and simulations. Not all collapsing cores produce single stars. In fact, most form binary or multiple systems. Two or more stars orbiting each other, born from fragments of the same collapsing core, or from the fragmentation of a protostellar disk. More than half of all stars in the galaxy are in binary or multiple systems. Single stars, like our Sun, are ironically in the minority. The distribution of stellar masses that emerge from this process is remarkably consistent. For every massive star born, there are hundreds of Sun-like stars and thousands of red dwarfs. Low-mass stars that burn slowly and live for trillions of years. Astronomers call this distribution the initial mass function, and it seems to be roughly the same in every star-forming region studied, from nearby clouds to distant galaxies. Why nature prefers to make mostly low-mass stars is related to how molecular clouds fragment during collapse, but the precise mechanisms remain an area of active research. Massive stars, though rare, dominate the appearance of stellar nurseries. They're incredibly luminous, thousands or tens of thousands of times brighter than the sun, pouring out tremendous amounts of ultraviolet light. This UV radiation ionizes the surrounding gas, stripping electrons from atoms, causing the gas to glow. The result is an emission nebula, those pink and red clouds visible in astronomical images, lit from within by the intense radiation of young massive stars. The Orion Nebula glows this way, powered by the trapezium cluster at its heart, a tight grouping of hot young stars that emerged from the nebula's core just a few million years ago. These massive stars live fast. Their immense luminosity means they burn through their fuel at prodigious rates. A star 30 times the sun's mass might live only a few million years before exhausting its core hydrogen and beginning its final evolution toward a supernova. They're already dying before their lower mass siblings have even settled onto the main sequence. And when they explode, they do so within the same molecular cloud that gave them birth, their shock waves slamming into remaining gas, compressing it, potentially triggering another generation of star formation. Meanwhile, the low-mass stars, the red dwarfs, settle into lives that will outlast the current age of the universe many times over. They burn so slowly, so efficiently, that they'll still be shining trillions of years from now, long after all the massive stars have died, long after the galaxy has run out of gas and star formation has ceased entirely. Every red dwarf ever born is still alive. None has existed long enough to die yet. Star formation in the Milky Way today proceeds at a modest pace. Roughly 1 to 2 solar masses of new stars are born each year, on average. That might sound like a lot until you realize the galaxy contains hundreds of billions of solar masses already. The current rate means it would take hundreds of billions of years to double the stellar population at this pace, far longer than the age of the universe. Star formation has slowed. The galaxy's youth, when gas was abundant and collisions frequent, produced far more stars per year than we see now, but it hasn't stopped. Across the galaxy, and clouds scattered along the spiral arms. The process continues. The Eagle Nebula, with its famous pillars of creation, columns of dense gas sculpted by stellar winds, their tips glowing with the light of stars forming inside, is protected for now by the dense material surrounding them. The Carina Nebula, a vast complex of gas and dust, larger and more active than Orion, containing some of the most massive stars in the galaxy. The Lagoon Nebula, the Trifid Nebula, dozens more visible to telescopes, each one a factory turning gas into stars. And scattered throughout these regions are the dusty cocoons where the youngest stars hide, visible only in infrared light. The Spitzer Space Telescope, operating in infrared wavelengths, revealed populations of protostars completely invisible optically, still wrapped in their birth clouds, slowly gathering mass. The James Webb Space Telescope, with its exquisite infrared sensitivity, is now peering even deeper, watching stars form in regions previously too obscured to study. The Sun itself was born this way 4.6 billion years ago, in a stellar nursery, not unlike Orion. That cloud has long since dispersed. The massive stars that formed alongside our Sun have already died. Their material returned to the interstellar medium, recycled into newer generations. The Sun and its surviving low-mass siblings scattered across the galaxy, their family ties severed by time and motion. But somewhere in the Milky Way, in clouds we can observe right now, stars are forming that will outlive the Sun, stars that will still be burning long after our world is gone, carrying forward the galaxy's story into futures we cannot imagine. There's something profound in watching these nurseries through telescopes. You're not seeing ancient light from the distant past. You're watching creation happen now, in cosmic terms, star formation unfolding over timescales of mere millions of years. In some regions, stars that didn't exist when humans first looked up at the sky have since ignited. In others, stars that glow faintly today will blaze brightly a million years hence. The process is continuous, patient, and utterly indifferent to our observation. Once born from those cold, dark clouds, once ignited into nuclear fire, stars begin their lives. And like all living things, their fates are written at birth, determined by a single fundamental property: mass. A star's mass dictates everything that follows: how hot it will burn, how long it will live, how it will die, and what it will leave behind. The galaxy is filled with stars at every stage of this journey, from newborns still clearing away their birth cocoons to ancient remnants cooling slowly in the dark. And understanding their lives means understanding the great cycle that shapes the Milky Way itself. Most stars spend the majority of their existence in a phase called the main sequence. This is the long, stable period when they fuse hydrogen into helium in their cores, converting mass to energy according to Einstein's famous equation. The energy released creates pressure that pushes outward, balancing gravity's inward pull. This equilibrium is remarkably stable. As long as hydrogen remains in the core, the star maintains this balance, shining steadily, changing so slowly that over human timescales it appears eternal. For the smallest stars, the red dwarfs, this phase can last trillions of years, These dim, cool stars, with masses less than half the sun's, burn their fuel so slowly, so efficiently, that they'll outlive almost everything else in the universe. They're so efficient that they mix their entire mass through convection, bringing fresh hydrogen from outer layers into the core where it can be fused. This means they can burn nearly all their hydrogen, not just the small fraction in the core. None has died yet. The universe, at 13.8 billion years old, is still too young. Every red dwarf ever born is still on the main sequence, still burning, still glowing faintly in the dark. Stars like our sun, mid-range in mass, burn faster, but still enjoy long lives. The sun has been on the main sequence for about 4.5 billion years and has roughly another 5 billion to go before its core hydrogen runs out. During this time, it's been remarkably stable, brightening very gradually, but maintaining nearly constant energy output, a constancy that has allowed life on Earth to evolve without catastrophic disruptions from the star itself. But hydrogen doesn't last forever. When the core finally exhausts its fuel, unable to fuse any more hydrogen into helium, the balance shifts. The core, no longer generating energy, begins to contract under gravity's pull. This contraction heats it, and that heat radiates outward into a shell of hydrogen surrounding the now inert helium core. This shell, heated from below, begins fusing hydrogen, and the energy it produces is tremendous, far more than the star generated during its stable main sequence phase. The result is dramatic. The star swells. Its outer layers expand outward, pushed by the increased energy flowing from that hydrogen-burning shell. The sun, when this happens, will grow to perhaps 100 times its current diameter, becoming a red giant. Its surface will cool, glowing red instead of yellow, but its total luminosity will increase enormously. Mercury will be engulfed. Venus will be consumed. Earth, if it survives, will be scorched lifeless. Its atmosphere stripped away. Its oceans boiled into space. The night sky from Earth, if any world remains, will be dominated by a vast red sphere stretching across the horizon. During the red giant phase, the core continues contracting, growing hotter, until finally it reaches a critical temperature, around 100 million degrees. At this temperature, helium itself can fuse, 3 helium nuclei combining in a process called the triple alpha reaction to form carbon. For stars slightly more massive than the Sun, this ignition happens suddenly, explosively, in what's called a helium flash. Billions of years of accumulated helium ignite simultaneously, releasing tremendous energy. But this energy is absorbed by the surrounding stellar material, not ejected, and the star settles into a new equilibrium, burning helium in its core while continuing to burn hydrogen in a shell. This phase is shorter. Helium fusion doesn't last nearly as long as hydrogen burning. For the Sun, perhaps 100 million years. When the helium runs out, the core contracts again. But for stars of the Sun's mass, that's the end. The core never gets hot enough to fuse carbon. The temperature and pressure required exceed what can be generated in a star of this size. What happens instead is a kind of gentle disintegration. The outer layers, no longer supported by fusion energy, begin to drift away, pushed by radiation pressure and stellar winds. These layers don't explode. They simply float outward, expanding slowly into space, forming beautiful shells and bubbles of glowing gas. We call these planetary nebulae, though they have nothing to do with planets. The name comes from their appearance through early telescopes, where they looked like the disks of planets. In reality, they're the final breath of dying stars, layers of atmosphere shed into space, ionized and lit by the ultraviolet light of the exposed core beneath. And that core, no longer burning, becomes a white dwarf, an ember of carbon and oxygen, roughly Earth-sized but containing perhaps half the Sun's mass. The density is staggering. A teaspoon of white dwarf material would weigh tons on Earth. This density is not maintained by fusion or pressure, but by quantum mechanics, specifically electron degeneracy pressure, a consequence of the Pauli exclusion principle that prevents electrons from occupying the same quantum state. This pressure is enough to hold the white dwarf up against gravity, but it generates no energy. The white dwarf simply cools, radiating its stored thermal energy into space over billions, eventually trillions of years, slowly fading from white to yellow to red to black, becoming a black dwarf, a cold, dark cinder drifting through the galaxy. Massive stars, those more than about 8 times the Sun's mass, follow a different, more dramatic path. They burn faster, living not billions but millions of years. When they exhaust their core hydrogen, they too become red supergiants, swelling to enormous sizes, some growing so large they would reach beyond Jupiter's orbit if placed where our Sun sits. But their greater mass allows them to reach higher temperatures, and they don't stop at helium. They burn helium into carbon and oxygen. Then, as the core contracts again, carbon fuses into neon and magnesium. Neon fuses into oxygen and silicon. Oxygen fuses into silicon and sulfur. And finally, silicon fuses into iron. Each stage burns faster than the last. Hydrogen burning lasts millions of years. Helium burning, hundreds of thousands. Carbon, thousands. Silicon fusion, the final stage, lasts only days. The star becomes layered like an onion, shells of different elements nested inside each other, each shell burning its fuel while supported by the heat from below. But iron is the end of the line. Iron is the most stable nucleus. Fusing iron into heavier elements doesn't release energy, it consumes it. When the core fills with iron, fusion stops. There is no next stage. The core, no longer generating energy, no longer creating pressure to hold itself up, collapses. In less than a second, the core implodes, falling inward at a quarter the speed of light. Electrons and protons are crushed together, forming neutrons. The collapsing core becomes a neutron star, a sphere perhaps 20 kilometers across, containing more mass than the Sun, held up now by neutron degeneracy pressure. The collapse releases an enormous amount of gravitational potential energy. The outer layers of the star, still falling inward, hit the rebounding core like a hammer. The collision reverses their motion, sending a shock wave exploding outward. This is a supernova, and for a brief time, it can shine as brightly as an entire galaxy, releasing more energy in a few weeks than the Sun will emit during its entire 10 billion year lifetime. The explosion ejects the star's outer layers into space at thousands of kilometers per second. These layers contain all the elements forged during the star's life and in the explosion itself. Carbon, oxygen, nitrogen, iron, gold, platinum, uranium, everything heavier than helium, scattered into the interstellar medium, mixing with the hydrogen and helium that were already there. This enriched material will eventually become part of new molecular clouds, new stars, new planets. If the collapsing core is massive enough, even neutron degeneracy pressure cannot stop it. The collapse continues beyond the neutron star phase, and the core becomes a black hole, vanishing behind an event horizon, adding another dark point to the galaxy's population of invisible gravitational wells. The supernova remnant, that expanding shell of ejected material, continues moving outward for thousands of years. The Crab Nebula, visible today in the constellation Taurus, is the remnant of a supernova that exploded in 1054 CE, observed and recorded by Chinese and Arab astronomers. Nearly 1,000 years later, it's still expanding, still glowing, powered now not by the explosion's heat, but by energy from the pulsar at its center, a rapidly rotating neutron star that beams radiation across space like a cosmic lighthouse. These deaths are essential. Without them, the galaxy would remain forever composed of hydrogen and helium. There would be no carbon to form the basis of organic chemistry, no oxygen to breathe, no iron to fill planetary cores and give worlds magnetic fields, no heavy elements to build rocky planets at all. The first stars that formed in the universe, those population 3 giants born from pristine primordial gas, lived, died, and enriched their surroundings, making possible the second generation, which enriched them further, and so on through countless cycles. The Sun is at least a third-generation star, maybe more. We know this because it contains elements that could only have been forged in previous stars and scattered by their deaths. Every atom in your body heavier than hydrogen was made inside a star, most of them in stars that exploded as supernovae billions of years ago, long before the solar system existed. Carl Sagan's famous phrase, "We are made of star stuff," is not metaphorical. It is literal. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in stellar cores and scattered into space by stellar deaths. The current rate of supernovae in the Milky Way is estimated at 1 to 2 per century. We haven't observed one in our galaxy since 1604, when Johannes Kepler documented a brilliant new star that appeared in the constellation Ophiuchus, shone brightly for months, then faded. Before that, Tycho Brahe observed one in 1572. And before that, the 1054 supernova that created the Crab Nebula. Statistically, we're overdue. Somewhere in the galaxy, hidden behind dust, or on the far side where we cannot see, supernovae have likely occurred since Kepler's time. We simply haven't detected them. When the next nearby supernova occurs, it will be spectacular. If a supernova exploded within a few thousand light years of Earth, it could be as bright as the full moon, visible during daylight, casting shadows at night. It would be a reminder, stark and beautiful, that the galaxy is alive with these transformations. that stars are dying right now, at this moment, somewhere among those hundreds of billions of suns. These explosions shape the galaxy structurally as well as chemically. The energy they inject into the interstellar medium creates hot bubbles, regions of shocked gas that expand, sweep up surrounding material, and can trigger new star formation by compressing nearby clouds. Multiple supernovae in a region can create superbubbles, vast cavities hundreds of light years across, where the gas is heated to millions of degrees. These structures drive galactic fountains, pushing gas up into the halo, where it cools and eventually rains back down onto the disk. The cycle is continuous. Stars form from enriched gas, live their lives burning through their fuel, die, and return that fuel, now further enriched, to the interstellar medium. Each generation builds on the previous one, slowly increasing the galaxy's metallicity, the fraction of elements heavier than helium. The oldest stars in the halo are metal poor, containing perhaps 1,000th of the heavy elements the Sun has. Stars forming today are metal rich, inheriting billions of years of accumulated enrichment. There's a poetry in this cycle, a rhythm of creation and destruction, birth and death, renewal and transformation. Nothing is permanent. Stars that seem eternal are temporary concentrations of matter that will eventually disperse. But nothing is truly lost either. The atoms persist, recycled endlessly, taking on new forms, new configurations, participating in new stories. You are part of this cycle. Every atom in your body has been through it multiple times, forged in stars, scattered into space, gathered into new clouds, formed into the sun and planets, and eventually into you. When you breathe, you exhale carbon that was once in a star. When you look at your hand, you're seeing matter that has passed through stellar cores, supernova explosions, molecular clouds, and now, temporarily, takes the form of flesh and bone before returning, someday, to the cycle again. And this cycle, this great wheel of stellar birth and death that has turned for billions of years, will continue. The Milky Way will keep making stars, recycling matter, building complexity from the ashes of previous generations. But the galaxy itself, vast and ancient as it is not eternal in its current form. Far beyond the stellar nurseries and dying giants, beyond the streams of consumed satellites and the dark matter halo, something approaches. Another galaxy, another great spiral of hundreds of billions of stars, drifting slowly closer through intergalactic space. And in approximately 4.5 billion years, it will arrive. The Andromeda Galaxy, Messier 31 in astronomical catalogs, though it deserves a grander name than a number. It hangs in the northern autumn sky, visible to the naked eye if you know where to look and the night is dark enough. A soft, elongated smudge in the constellation that shares its name, so faint you might miss it if you stare directly at it. Easier to see with peripheral vision, where your eye is more sensitive to dim light. That pale glow, that unassuming patch barely distinguishable from the darkness around it, is the light of approximately 1 trillion stars, a galaxy slightly larger than our own, lying 2.5 million light-years away across the void. 2.5 million light-years. The number is so large that it becomes abstract, loses meaning. Light, traveling at 300,000 kilometers per second, takes 2.5 million years to cross that distance. When you look at Andromeda tonight, you're not seeing it as it exists now, but as it appeared 2.5 million years ago, long before modern humans walked the Earth. The light reaching your eyes began its journey when our ancestors were Australopithecus, upright apes just beginning to use simple stone tools on the plains of Africa. That light has been traveling through empty space all this time, crossing the darkness between galaxies, carrying with it an image of a distant epoch, arriving here, now, to touch your retina and be translated into wonder. Under truly dark skies, far from city lights, Andromeda appears surprisingly large. If your eyes could see its full extent, the complete reach of its faint outer regions, it would span roughly 6 full moon widths across the sky. Most of that is too dim to see without long exposure photography, but the core, that condensed heart of the galaxy, is visible as a smudge, a ghostly presence that hints at something far grander than the naked eye reveals. For most of human history, we had no idea what Andromeda was. Ancient Persian astronomers noted it as a little cloud. Medieval stargazers cataloged it as a nebulous star. Even after telescopes revealed it as a spiral structure, many thought it was a gaseous nebula within our own Milky Way, perhaps a solar system in formation, glowing with the heat of its birth. It took until the 1920s, until Edwin Hubble's measurements of Cepheid variable stars within Andromeda proved it lay far beyond the boundaries of our galaxy, for humanity to understand what we were seeing. Not a cloud of gas, but an entire galaxy, an island universe, comparable to our own, but separated by unimaginable distance. And that galaxy is moving. Not away from us, as most distant galaxies do, carried outward by the expansion of the universe, but toward us. When astronomers analyze the light from Andromeda, they find it blue shifted, compressed to shorter wavelengths, the telltale signature of motion in our direction. The galaxy is approaching at approximately 110 kilometers per second, closing the gap between us at a rate that sounds dramatic until you remember the vast distance involved. At that speed, it's still approaching slowly enough that it will take more than 4 billion years to arrive. Why is it approaching? In most of the universe, galaxies recede from each other, space itself expanding, carrying them apart. But on local scales, where galaxies are close enough that their mutual gravity dominates over cosmic expansion, they can be gravitationally bound, pulled toward each other by their combined mass. The Milky Way and Andromeda, along with about 50 other smaller galaxies, form what astronomers call the local group, a gravitationally bound cluster drifting through space together. And within this group, the two largest members are on a collision course. This has been written into their motion for billions of years. Perhaps they've been approaching since shortly after they formed, their mutual gravity pulling them together across the void. Or perhaps they once orbited each other at a greater distance and are now falling inward. We can't reconstruct their full history with certainty, but we can predict their future with reasonable confidence. Barring some unexpected intervention, some massive third body passing through and disrupting their paths, the Milky Way and Andromeda will collide. The word collision conjures images of violence, of destruction, of catastrophic impact, like cars crashing or asteroids striking planets. But galactic collisions are not like that. They're slow, graceful, almost gentle despite the tremendous masses and forces involved. Stars are so far apart relative to their sizes that even when two galaxies merge, individual stars almost never collide directly. If you were somehow observing from a planet within one of the galaxies during the encounter, you would see the other galaxy's stars passing through the spaces between your own galaxy's stars, like two clouds of fireflies interpenetrating, mingling, but never actually touching. The first encounter will happen in roughly 4.5 billion years, though the uncertainty in that estimate spans hundreds of millions of years. As Andromeda approaches, it will grow larger in Earth's night sky, if Earth still exists, which is itself uncertain. The Sun will be nearly 10 billion years old by then, approaching the end of its main sequence lifetime, beginning to expand toward its red giant phase. Life on Earth, if it has survived that long, will be facing heat death from an aging sun, even as the galactic collision unfolds overhead. But imagine, for a moment, that Earth endures. That some far future descendants of humanity, biological or otherwise, stand beneath that sky and watch Andromeda approach. At first, it would appear as it does now, a faint smudge, but over millions of years, it would grow, brighten, resolve into structure. Eventually, individual bright stars within Andromeda would become visible to the naked eye. The galaxy would cease being a nebulous glow and become recognizable as what it is: a vast spiral of stars, tilted, approaching, filling more and more of the sky as the two galaxies draw within a few 100,000 light years of each other. Tidal forces would begin to distort them. Gravity pulls harder on the near side of each galaxy than on the far side, and this differential creates stress, stretching both galaxies along the line connecting them. Long streamers of stars would be pulled from the outer regions, forming tidal tails that extend for hundreds of thousands of light years into intergalactic space. These tails, visible in countless images of merging galaxies captured by Hubble, would trace elegant arcs across the sky, monuments to the gravitational forces reshaping both systems. The first passage might not result in immediate merger. Computer simulations show that often two galaxies pass through each other, their stars intermingling, but their overall structures maintaining enough coherence to separate again afterward. They would continue outward, slowed by their mutual gravity, eventually halt and fall back toward each other for a second encounter, and then a third. Each passage would further disrupt the spiral structures, scattering stars into increasingly chaotic orbits, flinging some into the tidal tails, while others settled into the growing combined core. During these passages, while individual stars rarely collide, the gas clouds within both galaxies would collide spectacularly. Unlike stars, gas clouds are large and diffuse enough that they can overlap, compress, shock heat to millions of degrees. These collisions would compress the gas, triggering enormous bursts of star formation, far more intense than anything currently happening in either galaxy. Thousands, perhaps tens of thousands, of massive stars would form in these compressed regions, igniting almost simultaneously, lighting up the merger with brilliant blue light. Within a few million years, Many of these massive stars would explode as supernovae, and for a brief period, the merging system would blaze with the light of countless stellar deaths, glowing perhaps 10 times brighter than either galaxy does alone. This starburst phase would be spectacular but brief, lasting perhaps a few 100 million years before the available gas was exhausted or blown away by the combined stellar winds and supernova shock waves. The night sky from any surviving world would be transformed. Bright star clusters, newly formed and glowing intensely, would appear scattered across the heavens. Supernovae would flare regularly, new stars appearing and fading over months or years. The familiar patterns of constellations would be scrambled, rearranged by the gravitational chaos, rendered unrecognizable. And at the center of this chaos, two supermassive black holes would be spiraling toward each other. The Milky Way's black hole, Sagittarius A star, contains roughly 4 million solar masses. Andromeda's central black hole is far more massive, approximately 100 million solar masses, a giant that has grown through billions of years of feeding and mergers. As the galactic cores merge, these black holes would sink toward the center of the combined mass, their motion slowed by dynamical friction, gravitational interactions with passing stars that gradually steal momentum and cause them to spiral inward. The final merger of two black holes of such tremendous mass would release more energy than entire supernovae, though not in the form of light. The energy would emerge as gravitational waves, ripples in space-time itself, propagating outward at the speed of light. These waves would pass through everything: Earth, stars, entire galaxies, barely noticed except by the most sensitive detectors. Future gravitational wave observatories, if they exist, might detect the signal, a slowly rising whoop of gravitational radiation as the black holes orbit faster and faster in their final death spiral before merging in a single, violent instant of space-time distortion. After multiple passages over the course of 2 to 3 billion years, the Milky Way and Andromeda would finally settle into a single, merged structure. The spiral forms of both galaxies would be lost, destroyed by the gravitational stirring. What would remain is an elliptical galaxy, a smooth, featureless ball of stars with no disk, no spiral arms, no clear rotational structure. The stars would orbit in random directions, some prograde, some retrograde, some plunging through the core, others looping far out into the halo. Order would give way to statistical chaos, though the system would reach a new equilibrium, stable in its own way. Astronomers have already named this future galaxy Milkomeda. A blend of both parent names is a portmanteau that captures the union of two systems, or sometimes Milkdromeda, depending on who you ask. It's a playful name for something profoundly transformative, but it acknowledges what this merger will create: a single, massive elliptical galaxy containing perhaps 2 to 3 trillion stars, one of the largest galaxies in the local group, dominating its neighborhood of space. The sun's orbit would be profoundly changed by all this. Currently, we circle the galactic center at 26,000 light-years distance, moving through the relatively calm suburbs. During the merger, gravitational interactions with passing stars and shifting mass distributions could fling the sun into a drastically different orbit. We might be thrown outward, becoming a halo star orbiting far from the merged core. Or we might spiral inward, settling into an orbit within the dense central regions where stars crowd far more closely. The odds of the sun colliding with another star remain vanishingly small even in this chaos, but our neighborhood would be utterly transformed. However, the sun faces a more immediate threat than the merger. In roughly 5 billion years, as its core hydrogen runs low, it will begin expanding into a red giant. Its outer layers will swell to perhaps 100 times its current diameter, possibly engulfing Mercury, Venus, and even Earth. This will happen around the same time as the Andromeda collision, perhaps slightly before, perhaps during. So, even if Earth's orbit survives the galactic merger, the planet may not survive the sun's evolution. The two threats, stellar and galactic, arrive on similar timescales, a cosmic coincidence that means any far future observers witnessing the merger will almost certainly not be observing from Earth's surface. This collision is not unique. Throughout the universe, galaxies merge regularly. Many of the elliptical galaxies we see in deep space are the products of past spiral galaxy mergers, systems that underwent exactly this process billions of years ago. We're seeing our own future written in distant galaxies, a preview of what the Milky Way and Andromeda will become. Major mergers like this reshape galaxy populations, transforming gas-rich spirals, actively forming stars, into gas-poor ellipticals, where star formation has largely ceased. The merger of the Milky Way and Andromeda is not the end of galactic evolution in the local group. Other members, particularly the Triangulum galaxy, M33, a smaller spiral currently approaching both the Milky Way and Andromeda, may also be involved. Triangulum might merge with Andromeda before Andromeda reaches us, or it might merge with the Milky Way-Andromeda system after our collision is already underway. The exact sequence depends on trajectories and velocities that are still being refined by observations. 4.5 billion years is an incomprehensibly long time. All of recorded human history spans perhaps 5,000 years. The entire existence of Homo sapiens, from the emergence of anatomically modern humans to the present, covers maybe 300,000 years. The dinosaurs, those ancient reptiles that dominated Earth for an entire geological era, reigned for 165 million years. Even that immense span, representing dozens of millions of generations of creatures living and dying, is just a tiny fraction of the time until the Andromeda collision. The timescale dwarfs everything we know, everything we can easily comprehend. Whatever witnesses this merger, if anything does, will not be human in any form we would recognize. It might be our distant descendants, evolved or engineered into forms adapted to radically different environments. It might be artificial intelligence, our created children, carrying forward some thread of our legacy into deep time. It might be entirely new species that evolve on Earth after we're gone. Or life might not exist at all in this solar system by then, extinguished by the sun's evolution, or by random catastrophe long before the galaxies meet. And yet, despite the vast timescale, despite the gulf of billions of years separating us from that event, it is already inevitable. It is written into the motion of the galaxies, into the gravity that pulls them together, into the trajectories they follow through space. Barring some unknown intervention, it will happen. The Milky Way and Andromeda will merge, two ancient spirals becoming one massive elliptical. They're billions of years of separate history ending in union. There's something both humbling and strangely comforting in this knowledge. We live in a temporary configuration, a moment in the galaxy's long story. What seems permanent, the Milky Way's spiral arms, its disk, its structure, is actually transient, lasting only billions of years before transformation. But the matter persists. The stars that currently belong to Andromeda will become our stars. The gas will mix. The dark matter halos will merge. Nothing is destroyed, only reorganized, transformed, made into something new. And through all of this, through the 4 billion years of approach and merger, the cycle of stellar birth and death will continue. Stars will form in the compressed gas of the colliding clouds. They will live their lives, burning hydrogen, creating heavy elements, and eventually die, returning their contents to the interstellar medium. The great wheel of stellar evolution that has turned for 13 billion years will keep turning through the merger and beyond, uninterrupted by the chaos, continuing its patient work of building complexity, one atom at a time, in a galaxy that will look completely different, but will still, in the deepest sense, be home. And so we return, from the distant future collision, from merged galaxies and transformed skies, we come back to here, to now, to this moment. You've journeyed tonight through the Milky Way, from the black hole's event horizon, where space-time curves infinitely, outward through the luminous bulge, along spiral arms lit by newborn stars, past stellar streams marking ancient violence, through the dark matter halo that holds everything together, and forward into a future where our galaxy merges with another to become something entirely new. But all of that, the past and the future, the vast and the ancient, exists around you right now. You are not separate from any of it. You are, in the most literal sense possible, part of the galaxy itself. Every atom in your body, with the sole exception of hydrogen, was forged inside a star. This is not poetry or metaphor. It is physics, chemistry, documented fact. The iron flowing through your blood right now, carrying oxygen to your cells, was created in the core of a massive star that exploded as a supernova billions of years ago, long before the sun existed. That explosion scattered iron across space, and eventually, after drifting through molecular clouds and mixing with other stellar debris, some of those atoms found their way into the disk of gas and dust that collapsed to form our solar system. They became part of Earth, and eventually, through an unbroken chain of geology, biology, and metabolism, part of you. The calcium in your bones, giving them strength and structure, came from dying red giant stars that shed their outer layers in planetary nebulae. The oxygen you're breathing right now, filling your lungs, entering your bloodstream, fueling the cellular respiration that keeps you alive, was fused from helium in the cores of massive stars that burned hot and died young. The carbon that forms the backbone of every organic molecule in your body, the fundamental element of life as we know it, was created through the triple alpha process in stellar cores when 3 helium nuclei fused under tremendous heat and pressure. You are made of stars. Not metaphorically, not spiritually, but actually, physically, measurably. You are a temporary arrangement of matter that was forged in stellar furnaces, scattered across light years, gathered by gravity into new forms, and shaped by evolution into something that can breathe, think, and wonder about its own origins. You are stardust that has learned to contemplate stars. The galaxy, through an unfathomably long chain of events, has organized some of its matter into patterns that can be observed, comprehended, and felt awe at the whole. You are, as Carl Sagan so beautifully put it, a way for the cosmos to know itself. Think about that for a moment. The atoms in your brain, firing in patterns that create thoughts and memories and consciousness, were made in stars that died before the Earth existed. Matter that once existed at temperatures of millions of degrees, under pressures that would crush any substance we can imagine, has cooled, traveled, combined, and arranged itself into neurons and synapses. The universe has become aware of itself through you, through us. We are the galaxy's way of looking at itself, understanding itself, mapping itself from within. We live in the middle chapters of the Milky Way's story. The galaxy is 13.6 billion years old, nearly as ancient as the universe itself. Our sun, at 4.6 billion years, is roughly a third the age of the galaxy, a middle-aged star in a mature system. We exist in a relatively calm period, neither in the chaotic early epochs when galaxies were forming through violent mergers, nor in the distant future when star formation will have slowed to a trickle and the galaxy will be fading, its gas exhausted, its potential dimming. We live in a time when the Milky Way is still active, still creating, but also stable, structured, settled into patterns that can persist for billions of years. This timing is not coincidental. It took billions of years for the galaxy to build up the heavy elements necessary for planets like Earth and life like ours. The first stars contained only hydrogen and helium, the primordial elements from the Big Bang. They had to live, fuse heavier elements, and die before the interstellar medium could be enriched enough to form rocky planets and complex chemistry. We couldn't exist in the galaxy's youth. There weren't enough heavy elements. And we won't exist in its far future when the sun has died and the merger with Andromeda has transformed everything. We exist when we do, because this is when the conditions allow for our existence. Our location within the galaxy matters too. We orbit 26,000 light years from the center in what some scientists call the galactic habitable zone, not too close to the core, where radiation levels are intense, supernovae are frequent, and gravitational interactions might disrupt planetary systems. Not too far into the sparse outer regions, where heavy elements are scarce and star formation is sluggish. We live at a radius where conditions are, perhaps not coincidentally, just right for complex life to emerge and persist. We orbit near the corrotation radius, where our speed matches the rotation of the spiral pattern itself, meaning we don't cross spiral arms frequently. We reside in a minor spur, the Orion Arm, a relatively quiet lane between major spiral arms. All of these factors, our distance from the center, our position relative to the spiral structure, our orbital speed, create an environment that has remained relatively stable for billions of years, long enough for life on Earth to evolve from single-celled organisms to conscious beings capable of understanding their cosmic context. The galaxy is our home. Not just Earth, not just the solar system, but the entire Milky Way. Everything we've ever known, everyone who has ever lived, every civilization that has risen and fallen, every thought that has been thought, and every emotion that has been felt. All of it has happened here, within this one galaxy, within a structure 100,000 light years across that contains hundreds of billions of stars. We have never left. We are part of it, embedded in its structure, moving with its motion, shaped by its history. And yet we are so small. One species among millions on one planet, among trillions orbiting one star, among hundreds of billions in a galaxy that is itself one among hundreds of billions in the observable universe. By any measure of scale, we are insignificant cosmic dust, a brief flicker of awareness in an ocean of matter and energy that existed for billions of years before us and will continue for billions more after we're gone. But there's another kind of significance, harder to measure, but no less real. We understand. In the 400,000 years or so that anatomically modern humans have existed, and especially in the last few centuries, we have figured out where we are, what we're part of, how the galaxy works, what our place is within it. We've traced our lineage back through biological evolution to the first cells, back through planetary formation to the solar nebula, back through stellar nucleosynthesis to the hearts of dying stars, back through cosmic inflation to the Big Bang itself. We know our story. That knowledge, that comprehension, that capacity for wonder has to count for something. We don't yet know if we're alone in this galaxy. The Milky Way might harbor billions of habitable worlds, and if even a tiny fraction of them develop life, and if even a tiny fraction of those develop intelligence, the galaxy could be teeming with consciousness, with civilizations asking the same questions we ask, looking up at their skies and wondering. Or we might be unique, the only place where matter has organized itself into awareness, the only eyes the galaxy has to see itself. The question remains open, one of the deepest mysteries we face. What we've accomplished in understanding is remarkable. We've gone from myths about spilled milk across the sky to precise three-dimensional maps of billions of stars. From thinking the Milky Way was the entire universe to knowing it's one galaxy among countless others. We've discovered the dark matter that holds it together, mapped the streams of consumed satellites, found the supermassive black hole at its heart, predicted its future merger with Andromeda. And we did all of this while trapped inside the very thing we're studying, embedded in the disk, surrounded by dust that blocks our view, unable to step outside and see the whole. That we've accomplished what we have is a testament to human curiosity, ingenuity, and persistence. But we still don't know everything. We don't know exactly what dark matter is, despite decades of searching. We don't know the precise mass of the galaxy or the exact number of spiral arms. We don't know the full history of mergers that built the Milky Way. or the detailed evolution of the central black hole. We don't know if life exists elsewhere in the galaxy or how common planets like Earth really are. The story is incomplete, and that's beautiful in its own way. There are still mysteries to solve, still discoveries waiting to be made by future generations who will know things we can only dream of. Right now, as you lie here preparing to sleep, you are moving through the galaxy. The Earth spins beneath you, rotating once every 24 hours. The Earth orbits the Sun at 30 kilometers per second, completing one circuit every year. And the Sun orbits the galactic center at 230 kilometers per second, sweeping through space on a path that takes 225 million years to complete. You have always been in motion, even in your stillest moments, carried along by these nested orbits, part of the galaxy's great slow turning. The atoms that make up your body are ancient and will persist long after you're gone. They're on loan to you, temporarily arranged in the pattern that is you. But eventually, they'll return to the cycle. When you die, whether tomorrow or decades from now, your atoms will disperse. Some will become part of the soil, part of plants, part of other organisms. Eventually, over timescales almost too long to contemplate, they'll return to the interstellar medium, perhaps through the Sun's eventual death as a planetary nebula, or through geological processes, or through events we can't foresee. And then they'll drift through space, perhaps for millions of years, until gravity gathers them into a new molecular cloud, a new stellar nursery, where they'll become part of new stars, new planets, perhaps new life. Nothing is created or destroyed, only transformed. The matter persists through all changes. Stars die, but their atoms continue. Galaxies merge, but their contents endure. You are temporary, a brief arrangement, a pattern that will dissolve. But what you're made of is ancient and eternal in its own way. There's comfort in this continuity, in knowing that you're part of something that has always been cycling, changing, renewing itself. You're not separate from the universe, but an expression of it, a temporary eddy in the endless flow of matter and energy. You live in a time when humans have figured out their cosmic context, when the tools and knowledge exist to understand where we are and how we got here. Not everyone in history had access to this knowledge. For most of human existence, people looked up at the Milky Way and saw mystery, told stories, wondered but didn't know. You get to know. You get to understand, at least partially, your connection to the galaxy, your place in deep time, your membership in a cosmos that is vast beyond comprehension, but also, in a strange way, intimate and knowable. The galaxy is a story, and every feature tells part of it. The streams drifting through the halo tell stories of galaxies consumed billions of years ago. The chemical abundances in stars tell stories of supernovae that enriched the interstellar medium. The warp in the outer disk tells stories of satellite galaxies pulling on our structure. The approaching Andromeda tells a story of the future, of transformation and renewal on cosmic scales. We're learning to read these stories, deciphering the history and fate written in the positions and motions of stars, in the light they emit, in the way they move through space. And now, as the night deepens, as your thoughts begin to soften and drift, remember where you are. above you, through the ceiling and atmosphere, through daylight if it's day, or darkness if it's night, lies the galaxy. A river of stars, a spiral of light, a structure so vast that light takes 100,000 years to cross it. It contains your past, written in the atoms of your body, forged in ancient stars. It contains your future, whether that's the next day or the next billion years when Andromeda arrives. You are part of it, not metaphorically, but literally, a small but genuine piece of something magnificent. Next time you see the Milky Way stretching across a dark sky, that pale band of light that gave the galaxy its name, remember that you're looking at home. Not a distant place, but your place. The structure you belong to, the pattern you're part of. And let that awareness bring not anxiety at your smallness, but peace, even joy. You're part of something grand, something ancient, something that will continue long after you're gone. That's enough. More than enough. The galaxy turns on, indifferent to whether you're awake or sleeping, indifferent to your worries or your joys. Stars are born in cold molecular clouds, slowly gathering mass until fusion ignites. Stars die in explosions or gentle sighs, returning their contents to space. Black holes spin in the darkness, warping space-time around them. Gas clouds drift and collide. Streams of disrupted galaxies wrap around the halo. Dark matter holds everything together with invisible gravity. All of this continues, has always continued, will always continue. A vast cosmic machinery operating on timescales that dwarf comprehension. And you, right now, can let go. You can release your grip on consciousness. Let your thoughts dissolve. Your breathing slow. Your muscles relax. The universe carries you. Gravity holds you to the earth. The earth carries you around the sun. The sun carries you around the galaxy. You're held by these nested motions, supported by forces you don't have to think about or maintain. You can rest. You are safe within the spiral arms, within the great slow turning of the Milky Way, within a story that began billions of years ago and will continue billions of years into the future. A story that includes you, but doesn't require you to stay awake. Sleep well. The galaxy watches over you, as it always has, as it always will. In the morning, or whenever you wake, the same atoms will form the same you, and the galaxy will still be turning, patient and eternal, carrying you forward through space and time. But for now, just rest. Be part of the quiet. Be part of the dark. Be part of the ancient, endless motion of stars and matter and energy flowing through the cosmos. You belong here. You always have. And that's all you need to know. Good night.